Ja, jag slog igång den där på en gång. Så att, god morgon alla glada. Good morning every happy one. Men det fladdrar alltså.
this one too.
And you see something on the screen also. Amazing. Well, I will try to fix our presentation here. So. Happy? Does something work?
Whoa.
So this is at my office. This is really. I've been meaning to ask for many years. How shall we pronounce your name?
Ragge.
Well, yeah, do it as just I will use reggae. Reggae? Yes. That works well. Okay. Yeah, I like it. It works. It's the easiest way to tell non-Swedish speaker about
I don't know. He's the expert. I'm a non-native speaker.
well, it's it works. Best to say. In Swedish, it just reggae. That's quite common.
Luigi.
Well, there is a guy that works or has worked at the IT department at KTH, the Royal Institute of Technology. That is also called RAG, and there have been lots of confusions. Okay. Did you ever come across him? No. I don't think so.
So why it
Well,
isn't?
we have a few minutes.
Yeah.
Like 10 minutes or something.
Yeah.
We'll see. There are actually some people that are interested in this.
It's one of the most interesting talks of the whole conference.
Well, I don't know. I just went into something really important.
But why are you bringing black and white pictures?
I think this is actually a photo of an English computer made in the mid-40s.
Okay.
It's from...
Yeah, you can tell from the analog meters below the.
yeah.
Yeah.
Well, actually, I did buy a bunch of these. Yes, I need that. I ordered from AliExpress. Yeah. They took $4 each. And I needed a bunch of meters for the power supplies and etc. Yeah. Why not?
Yeah, with it.
$4 inclusive.
Yes.
It's extremely cheap.
That's cool.
Chinese stuff is amazing. I will go to
Yes,
the
of course.
restroom
Yeah.
while people are coming up there.
It's muted, I think. No, it was the wrong. Ah. It works. Yes. Yeah, I tested.
We just wait a few minutes.
Ah.
Has anyone tried putting FreeBSD 8.2?
What did you ask?
I need our sync for 8.2.
Okay.
Happen to be still running an 8.2 jailbreak.
Well. Okay, I have no idea.
Can't help with EuroBSD1 or something. Yeah. No. No, it got destrays quite some time ago, but they made it built by default on ARM, I think. That was a big change. Most architectures still don't have it. Kirk is in the rep room. If you're looking for Kirk and the talk. Yes, we expect Kirk to have
But the topic of this talk is going to definitely be more entertaining.
Well, it might be. It's probably one of the most old speech that's ever been held at the
Yeah, that's good.
Jan asked me about.
We did switch with Kirk. He's in
Okay.
the red room down there.
Jan asked me if I had some projects or concerns or some presentations for the usual stuff or something. Well, basically presentations. And by some reason they was like, oh, we should hold this. Maybe you know more about it because I thought it was quite old now. I can wait.
Yes, odd is good. Odd at conferences is always good. Yeah. It attracts the odd people.
And whatever you say, it will be a hot topic. It will be a hot topic.
Yes,
At least warm.
yeah.
They are not that hot, are they? Like 70 degrees or something? They are not running that hot, I guess.
Altogether, they are going
Yeah.
That depends on you. They are like 1200 degrees inside to get
Yes, of course.
like emission water. So, and you need to keep the temperature of the tubes itself down below about 250 degrees.
Yeah.
Otherwise, they will start malfunctioning.
Yeah, but I thought in common operations they would do something like transistors, basically.
Well, they will do what is
And they will hover at a medium temperature of like...
yeah. Well, you need ventilation, otherwise they will get hot.
Yeah,
because
okay.
they are.
Yeah.
So, and I will mention a little bit about that also. You will
Okay.
have a heat dissipation of about 4 or 5 watts for each tube.
Yeah.
And you need a few thousand of them.
Yeah. Okay. Kirk is at the red room. Yeah, we swap switch. Yeah. I think we can start. Yeah. Okay. No problem. Okay, welcome to the first talk this morning. Anders is showing us his vacuum cube computer. I had hoped he would have brought it here, but apparently he displaced his carrier hoverboard, and so he couldn't bring it with him.
Thank you very much. I'll try to fetch. Sorry. Okay, you can hear me. Hello, everybody. It was quite some people that showed up here anyway. I was not really thinking that. Anyway, as you might know, I am not Kirk, so if someone has gone to the wrong presentation, you may
want to adjust that. I'm going not to talk about file system history. I'm going to talk about more ancient history, or almost more ancient history. Anyway, what is this I'm going to talk about? The nice pictures that we can see here is from an English computer made in the mid-40s. It's called EDVAC or something. And this is not my computer, but I would love to have something similar. We'll come to that later. Anyway, what I'm going to talk about, a vacuum tube computer, what the hell is that? As you may know or not know, that the semiconductor is a quite new invention, especially the transistor. Before that, computers were made using vacuum tubes. But after the invention of the transistor, that was patented in 1948, I think. Kirk is in the red room. In 1948, it took about 10 years to get something stable and working out of it, and about 1958, computer manufacturers started to use vacuum tubes instead. Started to use transistors instead of vacuum tubes. And I have a nice picture of a typical vacuum tube here. So, what do we know about vacuum tube computers? What do we know about computers at all? Well, one of the very early computerized-like things was the Babbage computing machine, designed in the mid of about 1850 or 1860 something. It was fully mechanical, didn't really work. I think it was never really implemented. Then relay computers came, and there was a bunch of them, quite good relay computers made as digital computers in like 1930s. Among the most famous there are the Z1, for example, the Konrad Zöse's machines. Never much known in the rest of the world because it was just coming up the war and he was living in Germany. He became manufacturing computers for Luftwaffe later during the war. But people soon realized that relays would be quite slow and started to try to produce digital computers, and this was during the war, so there were lots of money involved in this. Not a big problem to get money to finance things. And among the first computers, the first well-known computers, we should say, that is ENIAC. I will mention a little bit about that later. It was a very early project, and it was implemented using only ring counters. It worked like if you have seen an old mechanic calculator where you're going to move the handle around to multiply by 5 or 10, etc. It was implemented in the same way, which took a giant amount of tubes. There was also some English projects in the same area, especially to crack the German Lorentz crypto, which was, by modern standard, a modern crypto. It uses XOR of some semi-random numbers, and it uses prime numbers, I think, for calculating everything. It was quite modern, but they made the English people made a computer that could crack this by almost brute force, but it was trying around and found out how it should break it. And they were made about 8 or 9 of these machines. Then they told that all of these machines were destroyed, and it was secret. That's because the Soviet Union took these Lorentz crypto machines and used them in the East Bloc until 1960s. So the English intelligence, they kept a bunch of these machines to be able to crack the Soviet Union cryptos, because the Soviet Union didn't know it existed. Therefore, it hasn't been well known about these computers, the Colossus computers, until 1980s something. Anyway, in 1945, von Neumann wrote a description of how to build a computer. Well, actually, it was a bunch of paper collected from the University of, or I don't remember its name now, a bunch of papers that described how to implement a computer and that it should have data and code in the same memory of the von Neumann architecture, which later became more than just the basic layout. They also designed a complete computer with the instruction set and how you store words and all that, which was copied in a bunch of countries in Europe. It was, I think there were about 35 different computer models made by the same architecture. And I looked at it, and actually it's quite, to be something designed in the mid-40s, it's not worse than the 386 architecture. It's a little bit better, actually. So that was the basis about it. And this is one of the amazing things. We have something that is designed 70 years ago, and it's still the same way a computer works today. If you go look at the assembly code, it's the same way, but it's just smaller and faster today, but it's the same way it works. Nothing happens. So, well, I mentioned vacuum tubes a bunch of times. How many people here know actually what a vacuum tube is? Almost all. Some people think about it as something nicely glowing, ancient thing. You can see it in old radios. For people not so, people a little bit older, they may remember the TVs when you push the start button. So you wait 2 minutes and then you get a picture. Common in the 70s. We have the same problem today. We push on, or in the remote control, start it, and it takes a minute before we have got a digital encryption discussion, so we can see anything actually. So it's the same problem today. It takes a minute to start the TV, but not because of vacuum tubes. Yeah. I will give a little bit a brief description of how a vacuum tube works, because that's quite central to this. It began with Thomas Edison. While he was inventing the light bulb, he was trying to find out why the filament, the glowing thread in the light bulb, was breaking too often. And he found that he could get a current going if he put a plate inside the light bulb. He got a current from the filament over to the plate if the plate was positive related to the filament. If it was negative, nothing happened. Okay. Very interesting. What shall I use it for? Don't know, no use for it, but he patented it anyway. As he usually did with things back at that time. He had invented the vacuum tube diode. Nothing to use for anything really. And you can also see here, is there anyone that has a laser pointer or something? No, I don't have one. Unfortunately. We see. Do you have one? I love to be standing and pointing at things. So, where should I push here? Yeah. This is the symbol for a vacuum tube. This is a sketch of how it actually looked when he tested it. We have a plate, and here we have the cathode that is negative. And here is the more common version. He used the filament as cathode. Here we heat something else that emits electrons that goes over to the positive side. There are some benefits for having this not as the main cathode. And this is the reason why a vacuum tube glows. It can get really hot. Okay, that's a diode. Good to know. In 1907, it was a guy that he was named Lee de Forest. He discovered that if he could put a small grid, or like a small net, between the anode and the plate and the filament, he could control the current there. If the grid was becoming more and more negative, it would cut off the current. So it was some sort of way to control the flow of electrons. And it's only controlled, you have no currents on the grid, it's just the potential, it gets negative, and then it cuts off the current. And he realized that this could be used to amplify things. It will be a negative amplifier because you have an inverting amplifier. When you have more negative voltage on the grid, you get a higher voltage on the plate. Because you have, if you put a resistor in series with the plate, so and you cut down the current, you will get a high voltage there. So he used it to amplify things. And this is the triode. And the triode is merely the same as the diode, but we put a grid between there. This is just another symbol of it. Yeah. And he patented this, and now the things started to happen in the world, and people, not people, but big companies started to realize that they could actually use vacuum tubes for something useful, amplification and the music and all that stuff. So it came afterwards. So it started just before the First World War. And here we have, as I told you, a little bit different symbol, but it's basically the same. And we have the cathode as a rectangular thing here instead. There were lots of more different tubes made, but it's basically that you put in more and more grids that control different things. So these are the two basic things, the diode and the triode. Questions on the vacuum tubes and how they work. It's a little bit, not so little, but quite much electronics involved in all this. So we get back to this. They have built computers in the 40s, and in 1950s they even built faster computers, quite fast computers. And I was some time ago involved in a discussion with some friends. There might have been beer involved. I won't comment on that. And I was, after some discussion, I was pretty sure that it would be possible to make a computer by modern standards that could run a modern operating system, be internet connected and used as a web server by using technology from 1950s. And by reason I won't go into here, I had to prove it. And that is what I am currently trying to do. And I have tried to search around, but nobody has built a vacuum tube computer at all, as I can find, since early 60s there was still, but nothing else. And there have been other things. I found out there were some German guy that had built a digital watch using vacuum tubes that was dividing and doing all this. It was really nice things, but nothing as complex as a computer. And I should also note that I have never built a computer myself. I am not a big electronic building guy. I barely know so much, but there was internet, there are books, so I had to learn some things. Yeah. So, and it's we can say it's cool to do something like this because no one has done it for a very long time. Or warm. It can be very warm with these small glowing things. So, what can a vacuum tube computer do? See if this link works. If I can. What is this? It might be a little bit difficult to see here, but it's actually. Can anyone see what it looks like? Think you're driving in the night. It's how a big motorway were planned in Sweden. This is a simulation done on the first vacuum tube computer in Sweden, and it's the world's first computer simulation. It was the Swedish road company that wanted to get the driver's perspective of how the motorway should look like when it was finished. And I think this is like 60 years ago. So it's quite or 50 years to something. It's quite amazing anyway. So, you mean this? Then we do like that. So, they managed to make what's called animated films in the 50s on vacuum tube computers. Well, maybe encouraging. Well, we have a bunch of disadvantages with vacuum tube computers. There might be a reason people don't make them anymore. We have a pretty high power consumption. A vacuum tube itself, which usually contains 1 or 2 logic functions, it usually takes between 2 and 3 watts each to be able to just emit the electrons when it hits the cathode. And you will also have a loss of something called the anode resistance. You will have a loss of power in the anode in the vacuum tube, which may be something similar, about 2 watts, depending on the design. So we may have like a 4 watt we need for each tube. And if you have a computer and we have more than 10 logic circuits, we may have like 1,000 or something, or even more, then it will take quite much power. Fortunately, in Luleå, electricity is cheap. I checked before I left about the price, and it was just below 1 cent per kilowatt we pay there. We had to pay in June. That's quite okay. I can take quite much power from my computer without hurting my economy. No, I'm not surprised that Facebook placed a new data center only 2 kilometers from my house. So we will have something that is very warm. Everything that we burns up electricity, it will get heat of it. We need to get away with it. Same here. Luleå is not that warm, even in the summer, and especially in the winter it's quite cold, and I'm building things in my garage. I need to heat it, and I have electrical power there, so I can as well burn everything with instead of having the elements on, I can have a vacuum tube computer heating it up. Yeah. History says the tubes are unreliable. That is something that may or may not be true, depending on how you see it. A standard tube was designed to have a lifespan of 1,000 hours, and that was common through until they stopped manufacturing it. It's the same as light bulbs. A light bulb of the old types, they were, usually they should be running for about 1,000 hours. You had long life bulbs used in traffic lights, could run for long time. But in manufacturing process, they should be running for 1,000 hours. In a year, we have 9,000 hours, more or less. So we need something better. Long life tubes were produced back at this time to be able to, using computers that should be running for a long time, longer than just 1,000 hours. And the type of special quality tubes, they were much more expensive, but they work much better. So, but they didn't start produce the type of long life tubes until the actual demand came, which was when people started making computers. It needs a lot of space, and that may be a problem. As you know, a tube may be about 5 and 15 centimeter high and quite warm, and that is a problem. To be able to work, a tube needs quite high voltage. It's, I will talk about that in the design of the power supplies later, but it's plus minus 200, 250 volt is nothing strange. And it will be very, very high current. So it's, watch out where you're having your fingers. Yeah. And it has been, I have, we can say that I have had some discussions at home to be able to start building this. It's not sure that your wife approves that you want to put something big made of steel and everything that is warm and needs much power inside the house. Therefore I have it in my garage. You don't have a problem?
Can you use LEDs?
LEDs?
Simulated?
I could. I actually have a lots of. I have planned to have a lots of light bulbs and all that to have blinking licht. It should be some impressing. I have bought a bunch of things. I haven't. I can come back to that later. It should look. It must look cool. Otherwise, it's of no use. Well, I haven't found an advantage with building this type of computers. There are no advantages whatsoever. From sorry?
It makes for a great space heater.
Yes, but it's cheaper to buy an element to heat up. So it's well, it might be impressive for geeks like us, but I haven't found any big any advantage at all. So if someone comes up with something reasonable, I'm interested. It might be that the computer would survive an EMP. I don't know what how likely it is that we will get one, but don't say that. But I don't plan to run Windows on it. Okay, what speed are we speaking about? Here we come into my may or maybe not beer discussion. These are the speeds back in the time. ENIAC, as I said, it was a giant computer used ring counters, which means you have 10 tubes connected like in a ring, and you move a bit between them, which is a giant waste of tubes. Therefore, it had so many tubes and lots of germanium diodes. We were talking about semiconductors, and the transistor was invented in 1948, but we have had diodes longer than that. And I must note that it still exists manufactured. In 1934, they started manufacturing germanium diodes, which was useful for small radios, which are normal semiconductor diodes. It's cheaper to buy old stock of vacuum tube diodes than buying these. I will get back to that later, but germanium diodes, they have existed since the 40s, but since the 30s, but they are quite fragile compared to vacuum tubes. A vacuum tube, you can't hurt it electrically. It's very difficult to destroy it by connecting things wrong, overcurrent, and all that. Semiconductors, they blow out directly. Anyway, this machine did about 5,000 instructions per second. Very much at that time. Today, it's useless. I mentioned the IBM 604, which is a very nice thing. It's not really a computer, it's a programmable calculator. You did write programs on punch cards, you put it in and could execute them and calculate things. It did run about 10,000 instructions, calculations per second, running at a 50 kilohertz clock, and didn't have so many tubes. But the great thing with the 604 is that there are lots of information on the web that describe actually how to build the basic building blocks of a vacuum tube computer. They've made very good documentation, IBM, for the custom engineering, so I can recommend that. That was in 1948. Then there was the MIT Worldwide project. I am not really sure. I read a bunch of things that they got funding for this machine. It should be the fastest machine back then, and it was the first machine that had core memory, which we will also come back to later. I think that its main use was air traffic control or something. It did have about 5,000 tubes and run about 20,000 instructions per second. And then I also mentioned the Swedish computer BESC that came late 1953 and then was the world's fastest computer. That was the computer that had made the animated movie we watched earlier. I have read a bunch of things about that computer. It was the von Neumann architecture. It had about 2,400 tubes, and it did 25,000 instructions per second. This is not much. It would be very slow to run an operating system on 25,000 instructions per second, isn't it? Well, I think it might be done much faster, which is the basis for this. Vacuum tubes at that time were designed to be in radar system up to 250 megahertz or something. And it should be able to get them to run much faster, which I actually have tested later. So, to be honest, I don't know why they made their computers so slow back at these times. And I am sure I will design something that is much faster, or I have designed something that is much faster, but using the same technology. Well, I was not far into how to make things out of vacuum tubes. I was mostly arguing at the beer or not beer evening, but I decided that it should be possible to do. Well, I had to start to find out how do you actually design something using vacuum tubes. It's very simple. People didn't have calculators or anything back at the time. They used only things like this. This is a plate voltage current curve. And you can put a line in here depending on which current you want, which idle current you want, and how much anode voltage you want, and all that stuff. I won't go deep into how to design things. There are very good information on the net if someone, by some strange reason, get curious about it. I realized quite fast that it was quite simple to do something with vacuum tubes compared to semiconductors. This is the basis for, this is a curve that tells that if we have like 150 volt anode voltage, and we have, for this specific tube, if we have -6 volt on the grid, we don't have any current. If we instead have the 0 volt on the grid, and then we will get an enormous current if we have 150 volt. But then we have a resistor in series with the anode, and here is the engineering design process. If I decide that it should be about 50 volt when this is like 0, with 0 grid, I would end up here. We have 50 here, and this is the 0 crossing here. It will be about 6 milliampere anode current. And then I could put a line up here, and then I get the resistance I should use for anode. Quite simple if you get into it. So I have done this maybe 1,000 times, because these curves are different for different tubes. Not especially difficult. But I had to learn about this, and unfortunately there are information on the web, but not the basic books and all that. Well, I had to went to the library to find things from the 1950s and 60s to really understand how to do this. Then I needed to understand how I actually should do to be building something. This was my first project. It doesn't look so well on the, it's squeezed together in this direction, the picture. Well, anyway, this is a Class A amplifier. I thought an amplifier should be quite simple to do. A preamp and 2 tubes and an output transformer, and I designed it with this should be something like hi-fi quality, I thought. And then I connected what's called a harmonic meter and some input for it, and realized that, oh, it had gotten quite good. I have a total harmonic distortion at 5 watts of less than 0.1%. Hi-fi quality. And it was quite easy. So, it looks terrible, doesn't it? Yeah. It worked. Yeah. So, anyway, that was an amplifier. Here I need to build logic circuits and understand how to build these. These 3 are the basic logic circuits that are quite easy to build. I found. How many of you know anything about logic circuits? Almost all of you. Great. Yeah. Not the inversion, not the NOR. It's take input on that, either that or both, and get an inverted signal out. And this is an AND. 3 basic logic circuits. Okay, how do I build it with a vacuum tube? Very simple. This is the standard way of building an inverter. And this nice picture taken from the IBM 604 manual. We can see here if we give an input pulse here of plus 150. We have a 0 on 50 and 1 on 150. It will go through the diode here. It will take up the grid. And so we start getting some current, and we will get a dip in the anode voltage here, because the grid will get positive and the anode will get lower, and we get an inverted pulse out. We have just invented an inverter consisting of one triode, 3 resistors, and a capacitor, or 4 resistors actually. And you can also see that with the voltages, I mentioned high voltage, yes, minus 100 and plus 150, quite much. Well, we can take 2 of these and connect together in a very simple way. It's 2 inverters, but we connect to the same anode resistor, and then we get a NOR. If we get a 1 on either of these, we will get a 0 on the output. Because both here will use the same resistor and get the lower voltage out. So this is the standard, we can say the school example of how to build a NOR circuit with vacuum tubes. And an AND circuit, that is the last third part of it. Here I have another tube with multiple grids, but as I told you earlier, more grids you have more to control, only it doesn't change the function of the tube. Here we have 2 inputs, grid 1 and grid 3, both must be positive so that a current can go through the tube, which will lower the voltage on the output. We will get a NAND. And note that these are like one vacuum tube, 5 centimeter high, take 4 watt of energy for one function. Okay, we need a flip-flop. We need to store things in the computer. This is actually 2 inverters feeding each other, which may be seen if you did understand the earlier example. We take from the anode, we put into the grid on the other side. So either of these will be 1 and the other. So one will be one of the sides will be drawing current and the other will be blocking. And we can turn it over by having the input. We get a pulse, the input, a negative pulse. We will close down the tube that is conducting, and the other will start conducting. So this is the basic type of a flip-flop. And this has another very interesting property. If you could connect A and B to the same input signal, we will get a toggle. We will toggle it for each pulse. And that is quite useful. So I can note about flip-flops. This was patented in 1918 and called an Eccles-Jordan flip-flop, because they realized they wanted to store something in an electronic circuit. We can store a 1 or a 0. And so we are soon 100 years since the patenting of the flip-flop. Everybody looks here. No questions? Yeah. Yeah, it's just to break in and interrupt me if you have a question or a comment, or if you think I'm wrong somewhere. Okay, we have a bunch of problems with this. We have a bunch of high voltages that if I'm going to search, or if someone is going to search for an error in these circuits, you can just point in and see what's happened, because you have 150 volt here and minus 100 there and all that, so it will say and something will be smoking somewhere. It's dangerous to be in. In an inverting amplifier, we have something called the Miller effect, which is terrible, and I will describe more about that later. But it is if you are taking a voltage up and another voltage down in the vicinity of the amplifier, you will get an increase in capacitance, and capacitance is bad. This is a problem even in semiconductors where you have inverting amplifiers. And another problem is the gate propagation delay, which is partly due to the Miller effect. It has to do with capacitances in the circuits that from that you change the input from 1 to 0 or from 0 to 1, it will take a little while until it changes on the outside. And that's why we hate capacitances. Everyone in the computer world hates them, and I must say that most time I have spent dealing and trying to designing and calculating things in the computer has been dealing with how to avoid the problem capacitances. RC circuits, that is a circuit containing a capacitor and a resistor, they exist everywhere in the computers, and as you saw on the sketch, on the sketches I had earlier, there were one capacitor involved. That is to counteract for the capacitances inside the tube. Because we always get a capacitance between two elements that are reasonably close to each other. And this is not nice. And in a vacuum tube computer, we will have quite high resistances and low currents. That is terrible when you don't want so much when you want to get rid of the capacitance, because we have something called tau, which is a time constant you calculate to find how long time it will take for a capacitor to load up or load out a certain amount of voltage. And it's a natural exponent on this, and the tau tells when 63% more or less of the capacitor has been loaded or unloaded. And if we have, for example, an input on a grid, we can have a 500 kilo ohms resistance in the whole circuit, and we have 2 picofarad capacitance, which is quite common for the grid to the cathode. It will give 500 kilo ohms times 2 picofarad gives 1 microsecond in time constant. So if we suddenly lower the voltage on the grid from 0 down to, say, minus 30, the grid stops conducting at minus 10. Why I lower it down to minus 30, I will come back to that later. But it stops conducting at minus 10 and then waits for it to get up. It will take, if I have a design like this, it will take 1 microsecond, which is a very long time to get it up to start conducting again. That makes computers slow. So, how do we increase speed? You may be very well aware of, if you have been dealing with computers for quite some time, in the 90s it was very popular to overclock computers. You were overclocking computers, you got very hot CPUs, you had to get away the leads, the extra temperature, there were lots of problems with this. If we want to get rid of the problem with the capacitances, we need to get much higher current. And a tube is an inverting amplifier, but there is something called a cathode follower. And the cathode follower, it's actually an amplifier with just less than 1 in amplification effect. But it gives a much lower impedance output from it. And it works something like this. If we directly connect this to, if we say we have an input voltage here of 0 to minus 30, and we take the voltage here up to 0, the cathode will follow and be just about 0 also, and we have the load resistance on the cathode instead. And if we lower it to minus 30, it will lower the output to minus 30, so it will follow. We can have 2 of these, then we get an OR circuit. If either of these are tubes are taken up to 0 volt, we'll get 0 volt on the output. And that can be used to drive a diode logic, a diode. So if this would be connected to the input of the diode here, we will get an output here that would follow this, but we could also use it as an AND circuit if we have multiple of these drivers. The drawback with a cathode follower is that we will always be drawing current through the tube. That might be good also, but by other reasons, but it will take more current and the computer will take more energy and be warmer, because we will always be just burning up power here in the circuit. But it will be much faster. Have you ever heard about diode transistor logic? Something popular in 60s to get faster logic in computers? It was before the transistor, the TTL logic used DTL logic. It has some benefits in that it can be faster because it works in the same way with diodes, but it usually it burns up lots of energy. And it's the same here, but we get something that is much faster. And I'm focusing on this because this is the possibility to get lots of speed out of this type of computer. Okay, we go back to reliability problems for tubes. What are the main problems with tube unreliability? There have been lots of things written and research on this in this area of obvious reason, because this was what everyone was depending on back in the 40s, 50s. Yeah. And there are lots of documentation. The main problem are that the filament breaks. That the wire that glows up, that heats up the cathode in the tube, it breaks. Well, you can't do anything. It's like a light bulb. It's broken. You have to throw it away. But in the same way as if you have a light bulb and you never turn it off, it will light for a very long time, because it's the turning on and off that is the big problem. Same with vacuum tubes. So if you don't turn off the filament power, it will work. Another problem is something called cathode poisoning. Och a cathode poisoning is that impurities in the manufacturing process of the cathode, or actually the tube, may introduce a bunch of, you may have some particles in the tube that you don't want there. That will causes the cathode to stop emitting electrons. Or even worse, you will get capacitance inside the cathode, so that you will have an unexpected capacitance that will affect the performance of the tube, but if you check the tube, it will look all right. Another thing that causes this is that the tube is cut off. That means that you have you're not drawing any current through the tube for a very long time, which was quite common in computers at that time, because you did some calculations, then the computer stopped, and then all states on the tubes were at the same, maybe until next day when you started calculating again. And that implicitly burns out the cathode and may cause this type of cathode poisoning. This won't be a problem in a computer which runs continuously. If you have running an operating system, you will have things that it will do the whole time. You don't want it to go into sleep mode, because then you may get problem with the cathode and the electron emission. Exactly, something like that. Yeah. And then the last thing, we have the tube burn out. It has reached its end of life. We can't do anything about it. It's time to replace it. And this is something that can be pushed forward. Ericsson has written quite much of this, and I found a bunch of the reports I went through, and they found that tubes in some of their installations would survive longer than the actual telephone switch. As you know, Ericsson is the world's biggest manufacturer of telephone switches, and they had vacuum tubes of the same type actually that I'm going to use in my computer. They had vacuum tubes, and they checked, okay, this telephone switch, it's 12 years, we have to replace it with something new, but the vacuum tubes are still working in it, and it has been for 12 years. What did we do right here and not in other places? And it is a combination of that. You never turn it off, you have a constant current going through the tubes, etc., etc. Then tubes survive almost forever. So, okay, go back to, we have talked a little bit about this stuff now Oh, I may overshoot some minutes, hope it doesn't matter. This is what we did set up when I was discussing this. To be able to do it, I need to make a sane architecture. I want to be able to run something modern. I want 8-bit bytes. Especially I want some sort of bytes at all. For example, for Neumann architectures, they had 40-bit words using 2 instructions, 20-bit each. Well, it makes the other parts too difficult. I stay with the same architecture, but I want to be able to clock it at about 1 megahertz and take a few clock cycles per instruction. Then it will make a reasonable computer slightly faster than a bunch of PDP-11s that were quite common. But having this as an initial design goal, it is possible to clock it much faster. I have verified that, but I said that at the beginning. I have adjusted that later by other reasons. I need to have a reasonable RAM size to be able to store something in the computer, or to actually run our operating system. And I don't want to build a too complex architecture, no microcode, which means not an Intel compatible machine. Microcode is evil. Yeah. And I also want it to be modular. That means I can build parts of it and then extend it with more instructions, more things later. So that I don't have to finish everything at once. So, can I do something at 1 megahertz? Well, I built a small test thing here on this is Masonite. Do you know what it is? It's just a sort of pressed wood. I put a bunch of tubes in it and I connected it to some things. This is actually connected a stable multi-vibrator and a pulse shaper and a flip-flop and everything to get out pulses that are at each other megahertz, and they are a half a microsecond wide, so you have 1 megahertz feeding in and you split it down so you get it out each second pulse. Well, it looks quite well on the oscilloscope here, right? But it wasn't especially difficult to build, and especially in this environment, you're putting everything on wood. You get capacitances everywhere. It just sucked, but it worked well. 1 megahertz, nice, no problem. Okay, I have to select an architecture. I do not want, preferably not want to invent my own too much, even though I have to do modification. To be able to run some of our favorite operating system, I need at least something sane and a 32-bit target. MIPS might be possible. I've looked at almost all architecture I can think of. MIPS might be one of the closest because it's quite simple, but the current MIPS specifications are, there are too much peculiarities in it. Boring. But RISC-V was actually one that was modular enough to be able to deal with. And the pipelined architecture should play very well in this area. But I also realized that, well, I need to be able to implement this and this and this in the architecture to be able to do it. And especially 32-bit wide, everything 32-bit wide, it'd be very much soldering for not so much at the beginning. So I say I start with 16-bit. 16-bit targets, what do we deal with there? Obvious would be PDP-11. No, microcoded, won't do that. Nova was the best matching target. It has total of 22 instructions, which it's a load store architecture. It has load, store, jump to subroutine, and it has 8 arithmetic instructions, which actually are quite good because 8, that means 3 bits, they exactly in the instruction word matches 3 input points on the arithmetic unit in the computer. So it became very simple. But that also means that I had to go with 2BSD. Well, not a big problem. 2BSD is 211 is quite easy to port. So, There are a bunch of other things that I had to take in mind when doing this. Vacuum tubes, well, they are manufactured today. You can buy new vacuum tubes, well, it's quite expensive, and this is something I do. Nobody pays for it. I do it from my own wallet, and buying new vacuum tubes is not interesting, which means I had to stay with maybe not the best vacuum tubes everywhere, because I can't afford them. And also, I can't emit, at least right now, I can't emit so much power in the garage that I want to. I don't have that much power out there. As I said, they can be expensive. Transformers, we have lots of strange voltages, and these things are expensive. Therefore, I had to do a bunch of trade-offs in how I designed the actual computer. And to be able to keep the speed up, I need more of these cathode followers. If I don't do that, I can stay at 200 kilohertz and use the main logic. Then I can get something running and increase the speed later. Not a big deal, but I start from this part. These are the actual tubes. Nice pictures found on Google. These are the different types of them. The left one here is one of the rectifier tubes. The rectifier in this type of computer is actually a quite large part of the design, because there are a bunch of different constraints in how to make the computer run, or serve the computer with the correct types of voltages. And these are the names of the tubes. I also wrote some names about when it was invented. The double diode, 250 megahertz specification, 1939 it was presented. It can be used for these types of functions. Double diode for cathode followers, which I also use this for. Everything here is 1940. And in the power supply, everything is like 1930 or earlier. Yeah. I also note that this is the European naming of the tubes. Some of the tubes I use are American tubes, equal, but I use the European naming everywhere, just because it's simpler.
Any Russian tubes?
No, I have actually checked and tested, but the cheapest tubes I have gotten are from surplus sales in the United States. So here I found some place where I could buy them quite cheap. So I bought 3,000 of these because I realized that I would need a bunch of them. I don't want them to get lost. I bought them from a surplus sale in the United States, and I paid 20 cents each, which it's a reasonable price. And the same tubes or similar, newly manufactured, cost about €5 each. That might be good for a second or third version of the computer. I stayed with these, the cheaper versions so far. My wife was very suspicious when I come home with lots of boxes with this small tiny glass of, I don't want to know what you plan to do with this. Here is the basic construction of the basic parts of the computer that I need. And I have so far focused on how to design the CPU, and the other parts I will mention briefly, the CPU and the power supply. I have gotten an old military testing power supply that could feed almost any voltage, any currents, all that stuff that I got cheap on surplus sales, so I usually test with that. But I also designed power supply for this machine that could deliver. I haven't finished it yet. These are the main parts. We'll speed up a little bit there. In this computer, I need to use some voltage levels, and there are some different voltage level needed, and I had to decide about them quite early in the process to be able to use that in the design process. And here we have, for the logic part, we have two voltage levels. We have one that is the anode voltage, which is 150 volt, which is actually 130 volt. It has to do with idle current drawing in the circuits. Yeah, which is 130 volt high and 50 volt low. Yeah, which means at the grid I will have plus 5 volt high and minus 35 low. I may have told you that the tube itself, it cuts off current about 5-10 volts something in that area. Why do I go down to minus 35? Well, I've written it here. Current will decrease in the tube after a while when it has been running for quite some time. I don't know which time it will be or how it will work. I haven't built on the computer yet, but to take to be prepared for it, I decided to get it a much lower voltage, because this, if I don't get 5 milliamps here, this voltage will be higher, but it will still cut off the tube. So just to be careful if I have problem in the future. Yeah, well, here is the powers I've calculated that I should need at the CPU and the CPU only. We need stabilized 150 volt 5 ampere, quite much, for anode voltage, and I need about 1 ampere for screwing grids on the NAND tubes I have, and also about minus 100 volt and 4 amps. Use as a reference. And then I need a giant amount of power for the filament power. Yeah. And these, because I'm building with the technology at that time, I need to have both shunt and series regulator. Series regulators means that, and the shunt regulator both means that we will, if I feed it with like 200 volt, I will burn off everything between that and zero to just get lower voltage. It will just get burned in the air. Yeah. And this means that the PSU will be very inefficient from an economic perspective. But we can't do so much about it. That's how you design it. Yeah. And also, this is quite much. I have gotten some of the tubes, they can be connected in series, so instead of have 10 tubes at 6 volt filament voltage, you can have connected in series, you feed them with like 60 volt or 200 volt and all in series and connect directly to the power outlet in the wall. You don't need a transformer. Also here I am cheating a little bit. 3 and 5 volt can be found in a normal PC's power supply, which I have loads of. So I take it from there. No reason to buy transformers for it. So here was when I was taking out how I should place the PSU. Where I don't know if it's visible here. There are 3 rectifiers, the 1930s style, and 3 serial regulator tubes, and also some tubes for the actual stabilizing. And this PSU will be able to deliver a half amp at 150 volt, which means I need to build about 10 of them to just feed the CPU. And the size, 2 Euro cards, it will be a large power supply, and this is only for the 150 volt. I need the same for 75 volt and for minus 100. Well, we don't go deeper into that, we go into the CPU. Basic block of the CPU. Registers take at least 1 tube each per bit, which means we get lots of bits here. And registers and PC, they feeds a mux. So we have 2 muxes, push everything to an eventual inverter, an adder and a shifter, and then get out to get to memory and right back. This is the basic logic of the computer. Everything goes through the adder. It's very central in this, but also makes the design much simpler. And the individual parts here. Here is a part of the adder. This is 2 bits. It adds 2 bits. On one Euro card, it's a giant amount of tubes actually to just add 2 bits. But I made a design where I get a gate delay because you have something called a ripple carry. How many here know what ripple carry is? Yeah, that means when you add things, you get a carry out eventually, and you have to feed that into the next adder and next. So if you have 16 wide, you have a 16 wide bit wide bus, the carry will ripple from the first to the last, and you will have the gate delay in each place. I managed to get 7 nanoseconds per bit gate delay here, which I would say is extremely good, but it takes some power. But that makes a total ripple carry of 112 nanoseconds through the circuit. That would be very acceptable. That is actually very good if you compare to computers made of semiconductors in the 70s. They usually had a ripple carry time which was much larger than that. So I'm a little bit impressed. So. Anyway, we will have a hell of a bunch of tubes just for the CPU. So I just list here in all parts of the CPU how many tubes it's going to be. And I have a total of about 766 tubes. And I have also made a bunch of trade-offs that make the computer slower to not use so many tubes. But this is quite much for just the basic CPU logic. And you have 4 watts per tube. So we have 3 kilowatts we are using only for the CPU here, not counting the power supply. Choof! Another part of it, memory. Hell, I should design memory as it was back at that time. Which type of memory were actually used? Well, there were 3 common types of memory. One was the mercury delay line, used in UNIVAC used it, and there were a bunch of others using it. It means that you have a box of mercury, you send a signal in another end, it takes a while for it to go through it, and you get it out another end, and then you can take it, you let it go around. You use the delay time in the mercury box to store data. Can be used, I'm not sure, I'm quite sure Greenpeace would be quite angry at me if I should try to buy a bunch of what's called mercury. No, I don't think it's feasible. Williams memory, it's a normal CRT. You write things on the screen. If you put the electron, the beam there again, if it's written, nothing happens. If it's not written, you will get a pulse if you have some aluminium on the screen, on the front of the screen. So you can notice if you have something written or not already. These were quite normally used. They didn't store as much on the CRT as expected. There were like bit errors, and they had lots of problems with them. I have to go with ferrite cores. That's standard memory used until like mid-70s or something. Well, here is the comments about it. Core memory. It's very known technology. It's possible to get cores today, and they have some very special properties. It's or whatever it's called. It's the remanence. It's called in Swedish. It's that it stores the direction of the magnetic field in the actual core. I don't have a picture. Here I have a picture of core memory. This is a typical core memory size. This is 16 bits, 4 times 4. And 4 kilobit of core wouldn't take up much space. And there was a guy that made a core memory shield for Arduino. How many here know what an Arduino is? Oh, well, it's like a small program, not computer, it's a microcontroller, more or less. They tested core memory and found out that it still works. I have the URL if someone is interested in how to do a core memory shield to Arduino. I started calculating a little bit and realized that 96 driver tubes for quite much current could address 4 kilobit of core memory. Yeah. But it can address one or multiple planes. So 4 kilobit, it can be 4 kilobytes. You have 16 planes. You can have even more planes. You have some more difficult control logic, but it should be possible to get quite much out of it. Not especially difficult, but I don't need how to get this type of hard ferrites today. It was extremely common if you go back 40, 50 years. Now it's just soft ferrites you can find to avoid radio interference, not hard ferrites. If anyone has an idea, help is wanted. The same with manufacturing. I will speed up here. Input output. I use only serial ports. Very simple to build with vacuum tubes. If you're not running and especially fast. 900 baud, about 50 and 60 tubes. You have just above 100 tubes for it. Also, drum memory. But that's on the to-do list. I haven't decided yet how to do it. Here is how I want to have my utility room inside my house. It's still somewhat difficult. I haven't managed to convince my wife about it, but I'm planning to. So that's it. Pretty much it. Now we have taken over like 5 minutes or something. Sorry? Well, I hope, I hope I managed to get something useful out of this. I have realized that about 80% of all this is designing things and realizing that, finding out how everything should be connected and how it should work. Then the building part is quite fast. But the design phase takes an enormous time.
So what's the ETA?
I had planned to have, if it hadn't been for that I need to exchange my kitchen and all that stuff, I had planned to have around now a 2-bit computer working. It would work with 2-bit, and then it's just to extend the bus with. I also plan to emulate some parts of it by connected to a normal computer that could emulate like memory and all that stuff until I build it, so I can get some progress in it. Yes?
Do you have any kind of blog or anything where
Well, I wrote a web page about it. I haven't maintained it, so I haven't written anything there since January this year. But you can probably Google on vacuum tube computer or something, VTC1, or you might find it. I don't think, no, I didn't have a link to it. So that's pretty much it.
You're looking for a computer? Yes. Can I? Anyone got the spare computer to display a PDF?
You can have, otherwise you can use mine, it works.
Yeah, yes, please. Great. That's confusing. I got it. Success, yeah. I get plus minus when I do shit.
I've got one. No, where did it go? Oh well, whatever. Oh, I see. I uploaded it to the wrong server. Okay.
So, thanks everyone for patience. After the slight delay and tricky issues of getting the slides here, I'll pass directly on to Taylor, who's going to tell us about tricky issues in file systems.
Well, thank you. I am Taylor Campbell, Reastra in the NetBSD project, I actually got my start hacking NetBSD as a developer when fixing some issues in NetBSD's file systems in FFS and TempFS, and it turned out to be a bit of a rabbit hole. I assume you all know what a file system is. Standard Unix concept. There's this hierarchy of directories. There are regular files, device nodes, FIFO sockets, and stuff. Device nodes, FIFO sockets aren't terribly interesting. Directories and regular files are where it's at. Unix has this unified API for dealing with files in programs, file descriptors. And traditionally, in the file system, the format of the file system on disk, they're all represented by a single object called an inode. That is just, I don't actually know what the name stands for. I guess you had to have gone to Cook's talk to hear about that. Directories are a little bit different from regular files in that although regular files just store whatever strings of bytes users want to store, directories store strings of bytes that are semantically significant to the file system itself, and they figure into the operations that you perform on the file system in a more complex way. There's a standard set of file system operations, creating regular files, unlinking files, whatever kind they are, creating hard links between files, that is, creating multiple links to a single, well, just regular files, or maybe a few others, but not directories. Hard linking directories is really scary, I won't talk about that. Then you might also rename files, which turns out to be a great deal more difficult than it looks with its very innocent-seeming name here. Directory operations, all we care about is makedir and rmdir. You can also rename directories, but you can't link them. And then read, write, and fsync have to do with user data, not the file system's data, not the structure that the file system stores, but just whatever you want to put in a file. And there's also like make FIFO, symlink, and readdir for creating funny things called named pipes or FIFOs, and symlinks, which are pointers to files. And they're not very interesting. It's just you have to put something on disk and read it off at some point, and that's about it. So the reliability properties that we expect of a file system can be characterized by the traditional database transaction idea, ACID, that is atomicity, consistency, isolation, and durability. Although this term was invented in the databases world to apply to whole complex transactions that you might perform, for instance, inserting a whole bunch of rows into a table or updating a bunch of different rows in a table. With file systems in Unix, we usually care only about individual operations. That is, there is no standard API, no even common API for combining a series of operations in a transaction generically, so it doesn't matter what the operations are. There's nothing like that in file systems, and that's not what I'm here to address. It turns out that even getting the individual operations that I put above, getting these individual ones correct is hard enough. So the atomicity property is that when you perform an operation, such as makedir, it either happens all at once or not at all. You never wind up with, for example, a directory partially created but not actually put in any parent directory. Or if you want to do a rename, which is usually described as acting as though it were an unlink followed by a link followed by an unlink. That's never actually how it happens, because if the system crashed after the first unlink, then you wouldn't lose your file, unless the file was so new that it actually hadn't made it to the disk in the first place. But rather, the file system's job is to make sure that even if the system crashes in the middle of this, either you see the entire old state or you see the entire new state, but not something intermediate. Now, as a little aside, the POSIX standard doesn't actually mandate anything about what will happen if your system crashes in the middle. It is perfectly valid, according to POSIX, for the file system to replace your entire home directory by a collection of pictures of cats. But usually we don't consider that behavior to be very useful, and if the system crashes, we'd like to get a mostly nice state as a result and not have to completely reinstall everything and keep on deleting cat pictures, because we have plenty of them on the internet. We don't need any more on our file systems. The consistency property is that just every operation preserves a consistent disk state if it goes to completion. So if you make a directory, then that doesn't cause your system to be unable to boot afterward because there's something horribly wrong with it. A little more on this later. Isolation is that if two processes are trying to use the file system at the same time, then they won't see intermediate states while the other one is doing something, some complex operation. This is different from atomicity in that atomicity is about just a single process, really. I mean, you can extend it to multiple processes, but atomicity is the property that for a single process, if you crash in the middle and pick up again later, then that single process will not leave anything in an intermediate state. Whereas isolation is about multiple processes and no crashes. Just if two processes are running on different CPUs, they will always see a consistent disk state that is either before or after the other process's operation. Durability is the property that when the computer has told you that it has written something to disk, it is not lying to you. That is, when the sync program returns, and or when you're shutting the system down and it says syncing disks done, that means it actually is done syncing disks. And when you boot up tomorrow, it will still have the disks, still have the files and the data that you asked it to store for you. Now, a file system has usually one of three states. When it is just sitting idle and your machine is powered off and you shut it off cleanly, then it is in a clean state. You can just pick it up, you can mount the file system immediately and start using it, and you don't have to do anything extra to start using it. If it's in the dirty state, then you're in the middle of doing an operation on it, and this is when you actually have the file system mounted and you're using it and you're creating directories, writing to files, and it may be that if you take the current state of what is physically on the disk that is the backing store for the file system, when it's dirty, and you yank that out of the machine and put it somewhere else, it will take some work. It may take some work for the other computer that you put it into to pick up where you left off and then keep on performing file system operations. However, it will be able to do that. Similarly, if your machine crashes or you have a power failure, it should be able to pick up where you left off and not just lose all your files. It may lose some files that you created very recently, but it won't lose all the other ones. And then, if there are bugs in the file system, which invariably there are, or if there is a disk failure, which invariably there will be, or if a cosmic ray just flips a bit when you are trying to write something to disk, then your file system may be corrupt, and that's bad. And dealing with that depends on the severity of the corruption. I know there are companies out there that make a great deal of money trying to recover your very precious cat pictures from corrupt file systems or corrupt disks. But that's not the subject of this talk. I'm going to assume that there are no hardware failures, and I'll talk about how to avoid some of the bugs that will cause corruption. Now, most file systems have a little area on disk, or possibly several copies, several little areas where the data is copied, called the superblock. The superblock is just some metadata about the whole file system, and it contains various things. Usually it contains some magic number that identifies this is an FFS file system, or this is a ZFS file system, or whatever. It additionally has a flag in it that is the clean flag, and if the flag is set to 0, then that means that whoever last put the disk away, shut the computer off, or unmounted it, whatever, thought that the file system was definitely in a clean state, barring cosmic rays. If it's set to 1, then it is not known whether the file system is clean or dirty. It could be clean. It could be that everything has been fully synced to disk and it is totally clean state, except it was just not shut down properly. You yanked the USB stick out of your computer when you were before the OS had unmounted it, and so the information was not put on the disk that it is in fact surely clean. One could also mean that it is corrupt, but again, corruption, that's a side issue. The traditional way that that we deal with a kernel panic or crash or power failure while you are trying to do file system operations is fscheck. So traditionally, when you're doing a directory operation, for instance, when you're when you're creating a new file, you're allocating an inode, so you have to write some metadata somewhere into the collection of inodes in the disk. Then you also have to write a directory entry that points to the inode. These might be in very different parts of the disk, and you can't ask the disk to write those different parts simultaneously, atomically. What you can do instead, though, is guarantee that first, the order in which you write operations to disk will preserve a consistent state. So you might allocate an inode first, and then wait for that operation to complete. Wait for the disk to say, okay, I have written this new inode into the inode area. And then, once that happens, then you can insert a directory entry. Now this has the property that when fscheck, fscheck-p specifically, which is this the standard way that you run fscheck on boot, fscheck, if it finds a dirty file system, it can go through the whole file system and find, aha, this inode got allocated, but it's not pointed to by any directory entry, so this must have been an aborted create operation. So it never finished, the directory entry didn't get made, so this inode must not be important. So I will delete this inode, deallocate this inode, and then go on my merry way. As another example, if you want to write data to an inode, write data to a file, you just want to append something to a file, then you need to allocate some space in the data section of the disk. And again, this is traditionally how the FFS works. There are other file systems as well. This talk is mostly about the general FFS things and examples of FFS, but it applies to plenty of other things as well. So you need to allocate a block from the free list and mark that that block has been allocated in the free list so that it is not free anymore, so that nobody else will try to use it. But this just tells you that the block is allocated. It doesn't tell you who's using it. Then you need to update the inode to assign the block to the inode, and then the block is actually assigned, and after that you can use it. Now, each of these steps has to happen synchronously in sequence. Otherwise, the disk might reorder the writes to the actual spinning platter, or to the whatever it is inside an SSD, the chemical electronic state business. And if the disk reorders the writes, then you can get in trouble. So that's why we do these operations synchronously. So then, if we crash after the block has been allocated, but before it has been assigned, fscheck-p will scan all the inodes in the disk, and it will find all of the blocks that are actually assigned to inodes. Then it will scan all the blocks in the disk, all the data blocks in the disk, and find which ones are allocated. And if there are some that are allocated but not assigned, it will say, oh, this must have been an aborted attempt to allocate a block for an inode, so I will just mark this block free. Now, fscheck also serves to fix file system corruption. It is often discussed as, there are a lot of people who will tend to discuss fscheck as though its sole function is to fix corrupted file systems, and when you crash, your file system is always corrupted. But that's not true. There is a difference between a corrupted file system and a merely dirty file system, and fscheck tries to recover from both situations. fscheck-p recovers from a dirty file system, so you can keep on using it. fscheck in general also makes a best effort to try to fix corruption if it finds any, but it doesn't always work, and it's not always guaranteed to work, even as part of the contract of the program. So that's sort of a side issue that is helpful for if you actually do get disk corruption, it can help you recover from that. But that's fscheck working overtime, not its primary job. Now, doing a global analysis of the file system is slow. No doubt many of you have waited for a while for the machine to come up after a crash, waiting for fscheck to run, and as disks get bigger, the time it takes to do global analysis of the file system gets longer, as long as since the I/O throughput isn't going up as fast as disks are getting bigger. One approach to make it faster to go from a dirty state to a clean state is to use physical block logging, or to use logging, of which there are two main varieties, physical block logging and logical logging. So with physical block logging, instead of writing blocks synchronously to disk, that is, allocating a new inode, waiting for that to complete, and then updating the directory entry, rather, we write them serially to a log. We don't wait for them to complete before we write the next one to the log. Once they have actually been committed to the log, then we write the disks to write the blocks to disk in the real location. So we write a copy of every metadata block, one to the log, one to its real location. Then, once the disk has said, okay, it has been actually fully written to disk in the real location, then we can free some space in the log and reuse it later. After a crash, all that you have to do to get to the state that you are trying to get to, because there is a total order on the states that you put the file system into, the kernel will just replay all of the writes that have been committed but are not known to have completed to disk. This is a lot faster than fscheck because all you have to do is look at a usually several megabyte log at most. In NetBSD's logging, it's at most 64 megabytes, and that's good enough for many terabyte disks. All you have to do is look at those few megabytes and maybe write some blocks to disk, and that's it. You don't have to globally analyze the whole thing. Now, you can also, if you want to check for corruption, you could also run fscheck to globally analyze the whole thing, but that's not necessary for normal operation in the face of a crash of an unrelated kernel component or power failure. That said, physical block logging usually isn't enough to get all the properties you want, all the reliability properties you want. So another alternative is logical logging. That should have been logical logging, not logical block logging, because you're actually logging logical operations. That is, instead of writing the new 512-byte block that you're going to write to a specific location, you write a record saying, I want to rename this file to this location. And then you make a little transaction log of all of those. So when you're about to do an operation, you write a record of the operation to the log, then you wait for that to be committed to the log. Once it's committed to the log, you apply the operation on disk, and once it's committed to disk, you free the space in the log, and so on. It's broadly similar, but the details are very different. It's very different to write and implement, and it's more complex to implement. But usually you need at least a little bit of logical block logging in any practical system. So, for example, NetBSD's WAPBL, write-ahead physical block logging, is actually a composite of mostly physical block logging and a few logical logging operations. So, for example, if you want to delete a file, then you have to deallocate the blocks in that file. But if you deallocate the blocks and then reallocate them and give them to some other file, and userland tries to write data to the new file, there's no right ordering between the metadata blocks and the data blocks, so the user's write might actually hit the disk before the metadata update has been committed to the log. Now this is a separate problem. I'll discuss this issue in a little more detail later. It would be nice to put partial ordering between metadata and data updates, but that turns out to be difficult to engineer, and most operating systems and file systems don't actually do that. So, if another process writes data to the reallocated blocks, but the log entry didn't actually make it to disk, then when you replay the log, the deallocation might not have happened. And so when you wrote to a new file, that actually had the effect of writing garbage to the old file, and that's no good. So, in NetBSD's FFS, there's a logical log entry that says, I want to deallocate this file. Then NetBSD puts a whole bunch of physical log entries to actually do the deallocations, to update the block free lists and inode block assignments and so on. And once those are all done, then it goes and marks the logical block deallocation complete. Now there's some reliability assumptions that we make of the disk in order to provide the reliability guarantees I described before, ACID, to programs, to userland. Now, sometimes these assumptions are a little bit questionable, but usually we assume that if the OS asks the disk to write one 512-byte sector, then the disk will either write that 512-byte sector or not write that 512-byte sector. In the case of a crash, that is, if the OS crashes just after it issued a write to the disk, usually that write will actually make it to disk. There aren't all that many crashes that will prevent that from happening. If the power fails in the middle of writing that block to disk, that's a little bit more of a problem. In my laptop, I'm not usually personally all that concerned about such a situation because I have a battery and my OS knows to shut off just before the battery is empty, so that, or at least sync disks before and sleep before the battery is empty. So that's not an issue for most laptop disks. If you have a machine that has no battery, no UPS, nothing like that, that may be a problem. Another assumption that we make is about write ordering and the write cache. So to make things faster, disks will often queue up writes so that if it's on a spinning platter, if it gets a bunch of writes, if it can do a bunch of writes in sequence, that's a lot faster than a bunch of random writes. And so if it gets a bunch of random writes but can sort them into some sequential ones, that can go a lot faster. So a lot of disks these days have fairly large caches of blocks that they're planning to write to the actual physical medium, but that they have not written yet. If the power goes out when they haven't written them yet, then you might lose them. And that's a problem if the disk has already told the OS, oh, I've already written that. I'm done. It's done because it's cached, but it's not actually on the platter. In most operating systems, when you call fsync to ask the OS to please tell me, please write it to disk now, the actual spinning platter or the actual SSD, and tell me when you're done, usually when the OS tells you it's done, that means it's actually just in the right cache. And again, this isn't so much of a problem if you're on a battery and you can, gracefully shut down when you run out of power. And it's not really a problem with a crash because crashes of your kernel, of your OS, those don't affect the disk. The write cache is all inside the disk itself. But again, if you're not on a battery, maybe that's a problem. Most operating systems have another extra super fsync that will try to send a message to the disk to please empty your write cache and then tell me when you're done. But unfortunately, they're all different between different operating systems. NetBSD, there's fsync range. In Linux, there's sync data range or something. In macOS 10, there's an fcontrol call. It's a mess. And it'd be nice to fix that if someone wants to get on a standards committee. Not me. Something else that you might be concerned about with disks and file systems is confidentiality. So you might want to use disk encryption to make sure that if an attacker reads a snapshot of your disk, they can't get anything useful off it. For example, if you're going through airport security and you have brown skin and they think that you look sketchy because you go to hacker conferences, and then they might take your laptop and take an image of the disk inside. And you might not be too happy about that. So you might like to defend against that by using disk encryption. Now, disk encryption is easy, but it has it defends against a very limited threat model. It just defends against an attacker reading possibly several snapshots of your disk and doing nothing else. So it does not defend against an attacker modifying your disk at all. So when you get your disk back from airport security after they've confiscated it, restore from backups. Don't keep on using that disk. It's easy because you can encrypt the plain text and get a ciphertext that is exactly the same size. So when you have a 512-byte plain text block, you get a 512-byte ciphertext block, and that is writing that to disk is just as atomic as it would have been in plain text. If you're worried about an attacker who can modify your disk, that's much trickier. Now, in the case of airport security, the attacker could also open up your motherboard and put something funny in the firmware and mess with that in horrible ways. And so inventing some kind of disk authentication to defend against that, not so useful perhaps. But you could imagine using an iSCSI disk, for instance, and then talking over the internet, and maybe a man in the middle can intercept your blocks and mess with them there. The trouble is, if you want to do this at the disk level, not the file system level, but below the file system, you need to expand the plain text, expand the data to add some authentication tag, a MAC, or for example, an HMAC or something. And that means that either you have a really weird size of disk sectors for the file system, and file systems don't like that. They like power of two sizes. They usually assume 512 or 4096 bytes or something like that. Or you have to split your plain text disk sectors into somewhat larger physical disk sectors, and disks don't like that, and they will split things, and you lose the atomicity that you were hoping for. So you can address this at the file system level by having every pointer in your file system have an associated authentication tag that is the hash of some authentication tag, some secret keyed authentication tag for the block that it's pointing to. Then, if you ever want to rewrite a block, well, you have to follow down if there's a tree of pointers, then you have to follow down that tree and update every pointer along the path, which is maybe okay if you have a balanced tree of block pointers, and this is roughly how ZFS's file system authentication works. With FFS, that's not going to work so well, because FFS is not tree structured. FFS it just consists of a bunch of inodes sequentially and a bunch of data, and it's the directories are tree structured, but the metadata is not really tree structured. So returning to the write ordering issue, with traditional FFS, metadata writes are synchronous. You always wait for the write to complete before you're done. But data writes are asynchronous because, well, they don't really figure into the consistency of the file system structure itself, although as users we kind of care about that. And so this is a little bit of a problem. You can get synchronous writes by using fsync, but synchronous is not exactly what you want all the time. You usually want some partial ordering so that maybe you lose some data, but it doesn't get totally reordered and garbled. With a logging file system, you have serial metadata writes, but the data writes are usually still asynchronous. Now I want to emphasize here that logging doesn't increase the reliability of a file system. It just decreases the time it takes to start up again after a crash. If your file system got corrupted, logging or traditional doesn't matter, it's still corrupted. Now some file systems, like in X3FS in Linux, you can also log data. Most people don't do that because it's really slow and painfully, just too painfully slow to want to contemplate. But this, if you don't do that, it leads to a bug that has been around in FFS for a very long time that's very frustrating, and is why on my laptop I actually mount the file system synchronously so that all data writes are actually synchronous, which is okay because I have an SSD and it's fast enough for me. But you don't want to run your database cluster on synchronous file systems. So there's this bug that's been there forever, which is where if you allocate a free block to append to a file, then you write data to that block, and then you update the inode to point to the new block and say the file has gotten bigger. That sounds like it should be good, because then you always wait for the data to be on the disk before the inode says that here's the new data, except there's no ordering between A and B. So if you happen to crash after B happens, after the inode has been updated and the length has been increased, but before the new data have actually hit the disk, your file will appear to have whatever garbage was in the free block. If you additionally use logging, this can actually make the problem worse, because logging increases the throughput of the metadata operations because they're only serial, they're not synchronous. I had a particularly bad crash a few years ago when I was doing a CVS update of the whole NetBSD repository, and there was a crash, and pretty much every file in the CVS subdirectory, the CVS metadata had just garbage put in it. That was when I started using a synchronous file system on my laptop. Something else you might be concerned about with the file system is performance. And this is not just performance of the writes to disk, as in my laptop's is fairly slow compared to a lot of other things, but it's pretty safe. I haven't had any file system corruption for years. But you also need to worry about making sure that you're utilizing all the cores that you have in your machine. So if you have a big server and a bunch of people are doing rsync operations, and they're all in different directories, then you would like to be able to exploit the parallelism in your computer to let them use those different directories simultaneously. If you want to have the file system be correct, so that it provides the ACID properties, you need to have some kind of locking for the multiple cores. The easy way to do this is to have one file system-wide lock, giant lock. And that works, but your performance is crap. You cannot exploit parallelism. So you really want to have per object locking, that is per file, per directory, etc., so that an operation on one file does not block an operation on another file. This is where things get exciting with rename. So with rename, there are potentially 4 different objects that you have to lock. There's the source directory, there's the target directory, there's the source node, and there's a target node. Now you have to modify all of these potentially, because if you're renaming directories, for instance, you have to change the ... pointer of the nodes. And whatever you rename, you have to change the source directory and the target directory. Any 4 of these objects might be the same object. You could rename ... to ... and they're all the same. You could rename any horrible combination of things, and rename has to detect this, and do something sensible. It has to fail gracefully if you do something that is bogus. And since there are 4 objects you have to lock, they all have to be locked in a consistent order. In fact, every operation in the file system has to have a globally consistent lock order if you want to avoid deadlock. So this is a little bit tricky. Another thing is, you have to make sure that you don't create any orphan directory trees that are not pointed to by anything, because then you can't get at them anymore. And fscheck is not usually designed to recover from this situation. So if we have this little hierarchy here, with /home, /user, /var, and some user named foo, if we move /home under /home /foo, then we would no longer be able to get at that whole directory hierarchy, and it would be orphaned. So rename has to detect this situation and prevent it. So that means that rename has to do a analysis of potentially many objects, not just these 4, to make sure the situation doesn't happen. It has to walk up a whole directory tree, and then after it's confirmed that you are not going to rename something under itself, that has to continue to be true even if somebody else tries to mess with the directory hierarchy at the same time. So the traditional way to approach this in FFS is not. It sort of fails randomly. If you look at the code that was in NetBSD for a while, it was still in OpenBSD, I think, was in FreeBSD for a long time until, I don't know, maybe 10 years ago. It just sort of picks one to lock and then says, let me try to lock another one, and then if these things are the same, I'll bail, but if they're not, and it is very easy to, if the file system is not giant locked, to just run a program that will do lots of renaming and hammer on the file system and deadlock your kernel and corrupt your file system so fscheck can't recover, and you'll be a very unhappy sysadmin. What FreeBSD does now, or it does when I last checked, I haven't reviewed in a few months, but is it just picks an arbitrary order, source, target, node, directory, whatever, and says, lock the first one. Great, I've got it. Now, try lock the next one. And if I can get it, cool, try lock the next one. Can I get it? Cool, try lock the, oh, I cannot get the last one. All right, unlock, 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 unlock. Wait for that last one, and then when it's ready, okay, unlock that, and start over. And this doesn't actually guarantee you'll ever make progress. So there's a little counter where it says if there's a sysctl knob and it's set to like 100 or something, and if you try this 100 times and you couldn't make progress, then just give up. I can't manage it. Oh well. You can tweak this scheme so that you are actually guaranteed progress if you assign each rename operation a priority, and then whoever has the highest priority actually gets to make progress, whoever's waiting longest. This is, in a database world, this is called wait wound locks. Because you're waiting, and then if you're higher priority than somebody else who's just come in, you, I guess, wound them, and so they can't make progress. I don't know what the analogy is. In ZFS, it's a little more complicated, and I don't have time to go into that, so ask me later. But there are more locks, and it tries to lock them, lock a whole sequence of them going up the directory hierarchy, child first, not ancestor first. In Linux, which has had working correct rename for the past 10 years, thanks mainly to David Holland, who's an NetBSD developer, but told Alvira how to make it work 10 years ago. The lock order, in NetBSD, which has been doing this in FFS and TempFS and a couple others for the past 3 or 4 years, the lock order is ancestor first. Every file system operation locks an ancestor before it locks a child. There's only one rename in flight at any given time. Now, this is slightly, well, you might think at first that who would be doing a whole lot of renames all at once? And the answer is, well, rsync and tar, if you're creating a large file of directories, usually you want to write to a temporary file first, rename it to a permanent one. So it would be better if this were only one cross-directory rename in flight, because cross-directory renames are the only ones that can change the file system ancestry. Same directory renames, I think you can, I have not proved this, but I think that if you do a sort of reader-writer lock for renames so that readers are same directory renames, writers are cross-directory renames, then you won't get into any trouble. But I haven't proven this yet. So rename is tricky. Another thing that you might want to deal with in the file system is suspension. If you want to take a snapshot to do a backup or something, or if you want to just unmount the file system and wait for everyone using it to be done. When you're suspending a file system, you want to block new operations and then wait for all the existing ones to be done, to wait for them to drain. In NetBSD, we have an abstraction for this called fstrans, file system transactions. One way to approach this is to do a sort of recursive reader-writer lock, where every file system operation takes a reader lock, and if it already has one, then great, it's done. You can take it recursively. If you want to suspend, you take a writer lock, so then you have to wait for all the readers to finish up, and then no new readers can come along, and once the writer lock has been acquired, then nobody else is touching the file system. You can take your snapshot and start a copy on write thing and get a consistent snapshot. We use this in NetBSD for snapshots for backups. There's a generic system called fscow. But this scheme is, the scheme of using just a standard reader-writer lock is very slow, because then every file system operation has to take one global lock for the whole file system. That's a big point of contention. So what we do in NetBSD now with fstrans is we don't have a traditional reader-writer lock. Rather, we use what's called passive serialization. If you're familiar with Linux, then you might know about RCU, read, copy, update. Passive serialization is pretty similar. The difference is mainly that it was not patented, or rather, the patent expired long before the RCU patent expired. Otherwise, it's pretty much the same thing. So here, the reader doesn't touch any global state. It just creates a little perb thread structure that says, okay, I am currently in a file system operation. The writer then has to go through all the CPUs, all the threads, find out, okay, are there any operations going on right now? Then it can wait for all those to drain, and this way, although suspending is a very expensive operation, the file system operations themselves have very little cost. To my knowledge, NetBSD is the only operating system that uses this scheme. Solaris in ZFS uses a more traditional reader-writer lock, and I don't know how other systems do anything like this. I don't know how FreeBSD FFS snapshots work. Looks like I'm running out of time, so that's a hodgepodge of tricky issues in file systems that I've thought about. Any questions? Okay, I guess I must have been terribly confusing throughout the whole thing then, because surely there must be some unfinished business here. Yes, they are. They're also frustrating because if you break them, then people get really angry because you just corrupted their data, and that's bad. Yes, question?
I have to thank you for explaining the garbage handed at the right, because I've seen that and I've wondered what is it about. You said that logging probably makes it worse.
Yes.
And I suppose that also means soft updates.
Oh yeah, I didn't address that. So the question was, someone remarked that he was glad I talked about the garbage data appended after write because he's seen it and wondered what it was. And he asked, since I mentioned that logging exacerbates this problem by accelerating metadata writes, does soft updates, which is a scheme for partially ordering the metadata writes to a file system without a log, just maintaining a partial order in the kernel and not issuing new writes until the ones that they depend on have have completed. The question was, does that exacerbate the garbage data appended after crash bug 2? I think it probably does. I also don't really trust the soft updates code base in FreeBSD. NetBSD used to have it, and then we got rid of it because there were too many bugs and it was too hard to understand. So there may be other issues too, I don't know, but I think it probably does exacerbate that bug as well, because there's no metadata, there's still no partial ordering between data writes and metadata writes.
I think actually soft updates fixes that problem.
Oh, does it?
That the beat come after, or beat happens before A, in that case, it's because it's too slow to apply the sync, but soft updates ensures that the A, the inode update hits the disk, or it keeps everything actually more consistent. That was a kind of like a weak performance optimization in FFS, just because it's too slow to do it directly, like unless you do state flag amendments.
Right.
So it should not actually happen with soft updates. If you trust that, soft updates.
I think I have seen a problem with soft updates. It's means I'm using.
Okay. As far as I know, you should not.
So for the video audience, the comment was that he thinks that FreeBSD has fixed this issue in soft updates. Now, my question is, does it actually apply the same partial ordering to data updates and metadata updates?
It applies a slightly different order. I think you have to read the soft update paper.
Okay, apparently it's complicated.
There's a section in there that addresses this point.
Okay, I will have to reread the soft updates paper. I don't remember seeing a solution to this particular bug in it, but maybe I'm misremembering. It's been a while. Any other questions, comments, objections? Lewd Spencerian sonnets? All right, well, I guess that's it. Time for lunch now?
Okay. This one works. Want some special introduction?
No.
You can mute it up here.
Oh, okay.
Now it's on.
Yep, no, it is.
Okay, next talk is by Jasper, who will tell us about a tiny little insect called port roach.
All right. So, first a quick outline. I'll introduce myself as well as Portroach, brief history of Portroach and how it came to be. Then a bit about the present state of Portroach, as well as the impact it has on OpenBSD. Some future plans about, well, what I hope I can get into Portroach and what should get into Portroach at some point, given enough time. So for those of you who don't know me, I'm Jasper Adriaanse, an OpenBSD developer from the Netherlands. I've had my account for about 9 years now, and primarily I work in ports, and inside ports I maintain the GNOME desktop and the GNOME stack together with my co-maintainer Antoine Jacoutot. This started out, well, via work actually, since we do the OpenBSD desktops based on GNOME, as well as Puppet, which is another stack I maintain inside OpenBSD. So it's the Puppet master, the agent, the Puppet database, the whole ecosystem. And recently, so Puppet is all written in Ruby. And recently they had this genius idea to rewrite a pretty substantial component of it called Factor, which is a utility to gather system information, to rewrite it using C++11, which made it a lot harder to add new facts to it, since Puppet is not officially supported by Puppet Labs on OpenBSD. So it was quite hard to to understand C++11 and get it working on OpenBSD. So outside of ports, I'm working on the OpenBSD Octium platform, which is for the 64-bit embedded MIPS chips you find in the edge routers made by Ubiquiti. So first off, what is Portroach actually? It's this file scanner. And just to get some confusion out of the way, when I say port, it's an OpenBSD port from the port tree and not a platform. And a disk file is a archive or whatever format upstream decided to package it in. So it's a source file on an upstream mirror or primary fan-out site. So Portroach is written in Perl. And it does have a usable web front end that's basically static HTML, but it does some JavaScript fetching in the back. And for those who subscribe to it, they will get a daily reminder of whatever they claim to maintain has been outdated, as in there's a newer version available upstream. So why does Portroach actually exist? Well, frankly, because I'm lazy and I don't want to be subscribed to a gazillion of mailing lists in order to find out when someone releases a new version of their software. At least I've tried, and I think many others have tried to write a simplified Portroach that would just look at an HTTP or FTP mirror, do a directory listing, compare what's there as being the latest, compare it against the known disk file inside ports. And that works great for simple Apache-style directory listings, but it gets quickly out of hand when you have more complex versioning schemes that you want to compare against, and also when you want to talk to APIs of sites like RubyGems or npm.js, you cannot just get a directory listing from them. And secondly, there's some nice metrics you can get from Portroach. So on the main web page, it'll nicely show the number of ports it knows about, how many are outdated, and it also shows this information on a per maintainer level. So Portroach is actually based on Port Scout from FreeBSD, which I think was originally written by Sean, and it's well, their web front end is at portscout.freebsd.org. And back in, I think it was 2011, 2012, I first noticed PortScout and was really jealous about, well, FreeBSD having it and us not having a similar tool or even something that vaguely resembled it. So at the time I tried to get PortScout working on OpenBSD, spent half a day on it, couldn't get it to work and just gave up and subscribed to a few other release announcement mailing lists and forgot about it. Although in the back of my head there was still this idea or desire to have PortScout working on OpenBSD. So at some point I got, well, fed up with missing out on new software being released and not knowing about it, or having to go through all the ports that I maintain, which as a GNOME maintainer more easily runs into several hundreds of ports. And for GNOME it's easy since they release on a fixed schedule, so you know when you should be keeping an eye out on their master site and know when they're releasing new versions. But for a lot of other projects, it's mainly a manual task to keep an eye on what's out there and what's newer. So the initial support for OpenBSD was using make show, which fully expands the variable you request, whereas in PortScout it was using make -v variable -v another variable, which would not properly expand, and also chaining -v calls didn't work properly. So once I finally got over the hurdle of switching away from -v to show, I suddenly got, well, some results. And at that point it got enough results to have the rest of PortScout doing its thing, which is crawling master sites and compare the versions, since that's completely agnostic of whatever backend you have or whatever way you used in order to get the data into the database. So I submitted several pull requests to the forked repo on GitHub, which was initially created to add MySQL support, but the project on GitHub has been dead for, well, several years now, and those pull requests are still open since end of August last year, which is when I first started working on PortScout or PortRoach. So at that time it was not so much a fork of what I was working on, but rather, well, extending the FreeBSD project with OpenBSD support.
Was it always in Perl?
Yeah. Yeah, so PortScout was originally written in Perl, and PortRoach is still written in Perl. So as time moved on, I started to add more features to it, or initially ripping out features for things that OpenBSD simply does not have, like support for the moved file or master and slave ports. That's not existent on OpenBSD. We have other ways of sub-packaging or expressing those relationships. So at some point it started to diverge quite greatly from the original PortScout code, and after a quick IRC session with Antoine to come up with a new name, we settled on PortRoach, since it's this little tool that just crawls and crawls master sites. So at that point I also decided to rip out the FreeBSD support, since if I had to keep that, I would have to add a lot of if OpenBSD do this, else FreeBSD do that, which made the code, well, quite unreadable, even more unreadable. So that's also when I removed the XML data source. So PortScout, PortRoach has or had two ways of discovering data or backends, and one of them was a XML data source, which, well, I've got no idea how it was supposed to work, but since the other backend was simply named ports, it seemed like the most logical way to move forward. So at that point I removed all the FreeBSD compat and quirks and just made OpenBSD the primary OS to run it on and name it Portroach. So when I got a bit tired of working on the actual source of Portroach, I decided to flex my JavaScript muscle a bit and redo the web front end. So initially it was all static HTML generated by Portroach. Nowadays it's a lot more flexible. It's still fully static HTML, but there's a AngularJS through doing magic retrieval of JSON files that are generated by Portroach, which actually render the tables and retrieve all the information from, well, essentially the file system of the web server. So there's no built-in web server that does all the magic. It's just any web server that can serve static files can serve the Portroach front end. And a lot of, well, I guess you'd call it usability features were added. So searching would not require hitting enter when you would search for a maintainer. You just tap once, get into the search box, start typing, and all the matching results would remain in view, whereas all the other ones would be discarded. And also at this moment, Portroach still had support for MySQL, SQLite, and PostgreSQL. And since I've always used PostgreSQL, I kept focusing on that while keeping the SQLite backend, simply for the fact that it's easy to set up and do a quick test run. However, since Portroach is multi-threaded, it'll spin off 25 crawling jobs, and SQLite couldn't handle that very well, or rather not at all. So I focused on the PGSQL backend, and at the Ports Hackathon in Exeter, I decided to, well, as usual on a hackathon, come to a hackathon with a plan to work on X, and turns out you're just going to work on something completely else, completely different. And I wanted to work on something else and ended up spending a whole week working on Portroach. So that's actually when Portroach moved forward quite a bit. I think in about a week time there were 93 commits to the GitHub repository. And this hackathon took place in April, and from November the previous year I didn't have much time to work on Portroach. Also not much interest, because it worked good enough for basic results. However, there was still a lot of features that I wanted to add, or support for things that, or fix things that did not work at all. So I started by ripping out code that was never used or completely irrelevant, or stubs of code for things that I guess were meant to be developed further but never gotten there, like running it on multiple hosts. And that's also when the MySQL backend got removed, since it turned out it was not functioning at all. But the main piece of work I did then was to redo the way ports are discovered. So as I mentioned, initially it would use make show or make -v, and the way it worked, it would go to a ports tree, run make show for all the categories. It would go into a category, run make show again on all these subdirectories, and recursively go through all the ports it would find. However, sometimes it would miss a subcategory, or it would just take too long to go through the whole ports tree and run and make sure it's quite disk intensive as well. And the whole thing was too slow and too error prone for missing ports. So I knew there had to be a better way to discover the ports, since there are about 8,000 or 9,000 ports. And we've always had a tool called SQL Ports, which is essentially a SQLite database with all the ports information in it. For reasons unknown, I did not want to use it. I instead tried to write a discoverer of ports based on how SQL Ports discovered ports. Well, that of course went nowhere, and in the end I decided to just use SQL Ports since, well, it's there. And that actually cut down the time to build the initial database for PortRoach with all the ports that it should know about and the information it should know about, since it doesn't care what the comment of the files or the license or whatever. It just needs the master side, the current dist files, the maintainer, as well as the version, of course. So that sped up things, well, quite a bit. Currently a full PortRoach run takes about an hour and a half. That's including rebuilding the database, as well as doing the whole scanning process. And there was one thing that I could never get quite right, which was how to handle ports that have been removed from the ports tree, but they still lived on in the PortRoach database. So occasionally a maintainer would complain and say, hey, I got this email from PortRoach saying, well, my port that I maintained 7 years ago and that I removed 6 months ago is still getting upstream releases, and I still get notification emails about these new releases, but it's not there anymore, so why should I care, and why should PortRoach care for that matter? So using SQL Ports, it actually became near trivial to add support for that. And as I'll show in a future slide, the number of ports PortRoach knew about dropped because of adding support for removed ports. But at the same time, it increased by 2,000 or 3,000 ports just by switching to SQL Ports, because now it had a better way of finding all the ports that it would previously miss. So PortRoach works with what are called site handlers. So basically, when PortRoach does its checking part, it'll get a single port, get the master site, and then it'll query the registered site handlers, asking if any one of those can handle this particular master site. Which in the beginning, and I think PortScout still only has support for SourceForge, which when I picked up on PortRoach, that was actually broken since SourceForge changed its the layout of the XML file the site handler would use. They changed it, but PortScout was never adopted for it. And when I fixed that, it was actually a pretty easy fix, but all of a sudden PortRoach could get new versions of everything that was on SourceForge. So that was quite a big win. And then I set out to add a few more site handlers for sites that otherwise would be impossible to search, either because of robots.txt, which PortRoach honors, unless you tell it not to. But since it runs daily, you don't want to harass like an upstream mirror every day by ignoring the robots.txt, since it's there for a reason most of the time. So when a site handler gets a URL that it can handle, it'll tell PortRoach that it can handle it, and depending on the site handler and, well, by extension the site it's handling, the way of discovering new releases is much saner than the guessing that Portroach otherwise does. So the site handlers listed here are generally divisible in two categories, either those that get an XML or whatever listing with all the releases that are available for a project. For example, that's how the GitHub and Bitbucket, SourceForge as well, site handlers work. So they just get a list of all the files a particular project has released, and you sort of have to figure out what is actually a release and what is just a tarball that was put out for testing. The others tend to have a nice API you can talk to. So for example, the NPM site handler for the Node.js packages, you can just query the API and say, hey, what's the latest version of this project? And since it's such a structured site, you can just append the extract suffix, so .tar.gz or .whatever, to it, send it back to Portroach, and Portroach will compare that against the version it has recorded as being the latest in ports, and then the version comparison magic does its thing and either says it's the same as we have or it's newer. And if there's no site handler that can handle a site, Portroach will just fall back to guessing. Is the version that I have as current in OpenBSD ports, is that newer than the first one, the second one, the third one, etc., etc., comparing versions for every single file it finds. So that takes a long time, and that's why the site handlers are such a nice way of getting information about a lot more ports. And by every new site handler that was added, one moment please, for every new site handler that was added, you could see hundreds new ports or new versions of ports being discovered.
So a question I have, this might also apply to Postgres. There's also some logic in it that it fetches like the directory listing of the directory and does some snooping on that.
So your question is whether it fetches a directory listing and then does the, yeah, that's what it does. It's not actually going to get the file. It's just going to look at the listing. Otherwise it would have to, well, the bandwidth usage would be enormous.
Question. Have you solved the SourceForge problem of grabbing, say, an ISO from the funny SourceForge download, redirect, and all that stuff?
So I solved the SourceForge problem by, I think they have a RDF or Atom feed, something similar. At least every project has such a feed. And that's where they list all the files they release, which includes, for games, for example, you get all the data files in there as well. So for SourceForge, it's actually a bit harder to figure out what's new, since they put every single file they have uploaded. It's in the feed. So you have to try really hard to figure out what is actually a release and then to figure out, is it newer?
So maybe this name or something like that. I don't know how to open these reports, but these reports, because like the actual name of how the disk files we use that pattern on those.
Yeah, so the site handlers do get the disk name. It's also called like that in OpenBSD, which if the disk name is actually different from the disk file, for example, through redirect you end up requesting A but you get B back, that information is taken into account. So that's also how many of the site handlers query the upstream API asking for the project, since that's usually for the NPM, it's stripping off the node dash. For Perl, it's stripping off the P5 prefix. So the impact of Portroach on OpenBSD was quite noticeable. When the web front end was made publicly available on portroach.openbsd.org, all of a sudden you could see developers going through the list of ports maintained by ports@openbsd.org, which is the default maintainer set when there is no human maintainer. And you could see them go through a category just updating whatever was outdated. And people actually started to pay attention to, well, cruft or ports that had not been updated in years. But even though there was a newer version available, which is generally a sign that no one gives a rat's ass about this particular port. And you could see people actively removing stuff that fell into that category. So by now there are 21 registered maintainers to the daily email reminder, which is not a lot, but given the fact that there are not that many active ports maintainers, or ports developers for that matter, it's quite a good number, and more people sign up, well, not every day, but on a regular basis. So once the web front end started showing the some of the metrics back in October, I started graphing it with Munin, and the front end gives several metrics, so it's the total number of ports as well as the outdated number of ports. As you can see, the total number of ports increased slightly. There was a slight bump there that had nothing to do with ports, but just with a minor bug in port roach. As you can see, once the site handlers really started to find more and more new pieces of software, and people actually started to pay attention to it, the curve goes down, and as you can see here, it's the outdatedness of the ports tree in general. And there are several noticeable bumps and drops. So back in October, November, when it first started to work on the service discovery, that's when, well, of course, the graph starts. And the hackathon in Exeter, as mentioned, was around here. So the steep drop came from the fact that all of a sudden port roach could see a lot more ports in the ports tree thanks to using SQL ports. So, of course, the number of total ports available grew. People started to pay attention of updating ports, and the number dropped, well, quite a bit. And Antoine and I said at one point we should try to aim to stay below 18%, which at the time we were at 20-something%. So that accounts for several hundreds of ports that need to be updated. And I think currently we're at 16.5% or thereabouts. So we crossed our initial goal. Of course, there are a lot of ports that you cannot update because they change the API, and other ports cannot be updated because of that. So there will always be ports that are outdated, which is not a problem. And people should not blindly focus on updating ports for the sake of updating them. However, it does, well, make for some nice graphs. Only small gaps over there were due to the heat. I had to shut down the server that probed port roach for it. So that explains those gaps. That port roach was still functioning, Munin was just not getting any data. So port roach is not perfect, and it sometimes needs a, well, subtle or not so subtle hint what versions to ignore, or to ignore a complete port for that matter, or to use a different master site to actually query, rather than the master site that's listed as the master site for the port. So we use the port roach and port roach _ comment fields, which were inspired by the original port scout ports variable. And there are several ways to teach it how to compare versions or to ignore versions. So for example, the first line limits it or limits reporting new versions only to stable releases. So for example, this is also what we use for GNOME, since the 3.17 release is a development release and not something we want to be bothered by when they do a new upload with an odd version number, since it's not something we'll ever upgrade to. So by limiting port roads to even versions, we'll be sure to get updates on 3.16 and or 3.18. Sometimes you want to stick to a particular release line, in which case you use one of the other limit configuration options, and there are several other port roach pconfig flags, and they're described in the man page, but most of the time people would use these. And if it's not obvious why a particular port is being ignored, for example, or why there's a port roach annotation such as these, maintainers are often encouraged to add the explicit port roach comment. The reason why it's not a simple makefile comment is that this info is used and displayed in the web UI, where there's a listing of all the restricted ports, as they're called, and for those that have the port roach comment annotation, it shows why it's ignored. So obtaining port roach is, well, when you're on OpenBSD, trivial. You just pkg at port roach and run it. It's primarily developed on GitHub and not in the ports tree, since the ports tree is just getting the sources from GitHub. So the repository is there. Feel free to submit a pull request. So when you want to run port roach yourself, you can either run it against the entire ports tree, or oftentimes individual maintainers only are interested in ports they maintain. So you can simply restrict port roach to a given maintainer, a given category, or a given, I think it's only a single path you can limit it to even. So for example, you can only tell port roach to scan X11 GNOME, since the rest is irrelevant for that particular user. So when you first set up port roach, you have to set up the database, which is, if you want a real production run, use pgsql, and if it's testing SQLite, you do build, which is the stage where port roach queries the SQL ports database for any ports that may have been added or removed. The rebuild command is actually used to rebuild the database if there previously had been one, and query SQL ports for ports that are in the port roach database but no longer in the SQL ports database, and that's a sign the port has been removed, so we can drop it from the port roach database and completely forget about it. And then there's the most important part of port roach, which is to do the actual checking, which takes a bit more than an hour on the machine where it's currently hosted. It's portroach.openbsd.org. And to actually use the data, it's a simple generate command, which in port roach defaults to the dynamic, semi-dynamic JSON output and static HTML, whereas port scout only has the static HTML and I think an RSS feed as well that's available. That's something I meant to look at for port roach. I don't know if it actually works, the RSS feed, but there's a stub in there, and who knows if it actually works. So once the database has been built, it spawns off a number of threads, which is usually 25 or 20, unless you're using SQLite and you really want to limit it to a single thread, otherwise the database goes pear-shaped. So for each port it gets, it's just going to get the master site, the disk name, go to the upstream website if there's no site handler available that can handle that part, and I'll just do the same thing over and over and over for about 8,000 times. So interfacing with Portroach, the primary way to use it as a regular maintainer would be through the web front end. However, as I mentioned, there's, well, I wouldn't really call it an API, but there are JSON files available with the totals of all the ports, as well as a per maintainer JSON file, which is used by the get outdated script by Andrew Fresh, that will just for a single maintainer gets the outdated port for outdated ports for him. And in order to demonstrate the JSON files, I wrote a simple tool called CL Portroach, which is in Common Lisp. And it was just a way of playing with the JSON files and interfacing with them, see what can be optimized and what's actually missing. So one thing that's currently missing also from the web interface is a per category view. So for example, if you're only interested in the X11 GNOME category, you can, well, should be able to query the X11 GNOME JSON file and only get that information instead of everything for the whole tree or the maintainer. So this is also on GitHub. It's a very simple library where you can print this, the summary of the whole ports tree. So this one has, well, 7,500 unique ports. So a port in the ports tree can have multiple sub-packages, which count towards the total number of packages built, which is near 9,000. However, due to the fact that, well, the multi-packages or flavors or other restrictions, the total number of actual ports that Portroach knows about is 7,500. And of course, you can query for a individual maintainer as well. It's on GitHub, not available via QuickLisp, which is the Common Lisp package manager. And it's just Lisp, so it's very easy to read and understand what it actually does. Which may or may not be true for everyone, I guess. So Portroach currently works quite well, and it's progressed tremendously in the past year. However, there's still, well, some ongoing tasks. It's not perfect yet in finding all the ports that are in the tree. It misses some, and its handling of multiple disk files is not perfect either. So for example, a port can have, well, a pattern you see with a lot of games, they have the engine, which is a certain version, and the same port also has data files for the port. And currently Portroach only finds the first one, which would generally be the engine, and ignore any of the other disk files. So that's an area that could use improvement. The scanning part, that's the, not so much how SQL ports does it, but rather how Portroach uses the data from SQL ports. And finally, there's the version comparison, which is, well, a bit of black magic in ignoring some suffixes like -bin, how to handle release candidates, betas, alphas, or whatever upstream puts on their, well, FTP area, so to say. And of course, site handlers can always use improvements, as in new site handlers can be added for whatever site is denying regular crawling, or if there's an API. So the latest one that was added was for Bitbucket. Actually, the latest one was for Mozilla, which was contributed by Landry, the Mozilla maintainer in OpenBSD. So the Mozilla master site layout puts the version number 2 directories up. It's 1 or 2 directories up, and Portroach could not handle that. It would try to go 1 directory up, but not further, since otherwise it may end up crawling the entire website, which is, well, a waste of resources. So those are areas that generally need ongoing improvement. And there's some future plans or wild ideas that that I have. So one is to integrate DPB into Portroach, or the other way around, to integrate Portroach into DPB. So DPB is the distributed package builder that Mark Espy will speak about after me. And it provides a very nice engine for distributed tasks, so to say. Whether it's actually fetching disk files or building them. It also has a nice UI, since the output of Portroach, when you run it on the console, is, well, hard to make sense of compared to the UI DPB provides you with. So that's one thing, and it cannot be done right now, because SP has to handle some interfacing problems when you're actually outside of the DPB builder, so you cannot use parts of DPB right now inside of Portroach. But once SP handles that, it'll be easier to integrate. The front end, as I mentioned, could use a per category view, which there is basic support for it in the Portroach itself. It's just that the generated front end doesn't know how to parse that or to properly present it. One other thing is master sites disappear. They go offline, the domain expires, or for whatever reason, a master site can become unreachable. Currently, Portroach notices it, since it comes to a dead end at some point. It cannot connect, or for whatever reason, it cannot handle that port. And right now, that information is just discarded, and unless you're actually watching the Portroach console, there's no way of knowing that. So there's also no way the maintainer can know it. Of course, they can if they actually track upstream and know when something is being removed or goes dead. However, there should be a way for others to see this information as well. So another view would be helpful in that. Well, and tests. Currently, there are some very basic tests for the version comparison. It's the most easily testable part of Portroach, and that's, I guess, why there are those tests, which most of them came straight from Port Scout. Though there are a lot of other areas in Portroach that could use some instrumentation and proper testing. So, Portroach is the OpenBSD disk file scanner, forked from Port Scout. Currently, it's very hard to backport the OpenBSD specific stuff from Portroach to merge it back into Port Scout, if that moment ever came. However, the site handlers and the site handlers API is something that Port Scout can just copy one-on-one. Just drop it into the site handler directory, register it, and that's something that can be copied and integrated into Port Scout right away. There's the web front end, through which most people use it, the JSON API. That's not fully documented, but people have found ways to interface with it. And if the regular web front end is not something you'd want to use, you're free and welcome to write your own using the JSON files. So first, I want to thank Antoine for coming up with the Portroach name, as well as hosting the daily run Portroach instance on portroach.openbsd.org. Stuart Landry and Aaron for fixing my JavaScript gap of knowledge, as well as contributing ideas and site handlers, and EuroBSDCon organizers for getting me here. So, any questions or feature requests or? Interface? I've got a demo. I'll share it after the questions.
For Scout does it, but I need to see if there are any matching bottleneck reports or pixelizers.
I'm sorry?
Did that first approach discuss new version and can create a database of bug requests and things that like that also updates that port to that version. Does that know?
I'm not entirely sure I understand your question.
So that suppose GNOME 3.18 comes out and port approaches that's GNOME 3.18 and the maintainer, well, you in this case, yeah, you will submit it. Well, you make a Bixilla request to update GNOME to 3.18.
Okay.
What code see that request?
No, OpenBSD doesn't have a public bug tracker or a bug tracker at all, for that matter. So there's no way to notify a maintainer of that. Although the web interface, people can go through it and poke someone like, hey, you should update your GNOME stack. So that can be done. There's just no way, no official way of recording those.
Yeah, so I don't think Post Scout was it either, but that would fail to ask them, yes, I know there's an update.
Well, so the email reminders, they only get sent out once for any given version. So it won't send you daily harassment of, you should still update to 3.18, you should still update. No, it'll only say, oh, there's 3.18.1, you might want to update to that.
What happens when in a mirror site or a certain port appears a new file with a new version and then disappears?
The newer version, so if a upstream mirror releases a version and then unreleases it, which happened with OpenArena a couple of years ago, it'll just stay there as being newer in the database unless it's going to be explicitly ignored through a port roach annotation. I think it could be solved by doing like a clean run and just reinitialize the database, but that way you'd lose all the other information. So there should be a better way of discovering retracted versions.
So does port roach also automatically generate stuff like, say, like a disinfo snippet? So it says like, hey, there's a, like, when I fetch this, I got this checksum and this site, you smack this and you this on your port stream and use me.
So portroach does not generate an automatic disinfo snippet. It does not record the checksum at all of the files, simply because it does not actually download the file. It just gets the information of what is available rather than doing the download. However, it could be added, I guess, but there's not much, well, point to it. Since once the disk file has been recorded by the maintainer and committed, if upstream rerolls their release, you'll notice anyway. Okay, so I'll do a quickly show the. So this is the new web front end. So if I want to search for my own ports, if I type my name correctly, you can see that I'm slacking off a bit. I still have to update these ports. And these are some of the AngularJS improvements where you can toggle the display on the fly. And well, I mentioned the restricted ports. So there you can see why audio calt is at this particular version, because it's limited to this and only this version. And as you can see, all the GNOME-related things, they're explicitly limited to the even versions, since we don't care about the development releases. No more questions? Thank you.
Pretty bad in the fact that Template is doing the XML stuff. Okay. That gets carried. I see. GitHub.
Okay, this is working.
Check, check. Okay, works.
discover how they did this file system, assuming the maintainers have updated the ports. Mark is going to tell us how to quickly and securely rebuild the package.
Well, for a start, I should say that I'm probably guilty of not updating all of my ports recently because I've been busy with other things. But like Jasper and some other developers, we tend to maintain too many ports for one person. What I'm going to talk about today is something completely different. I'm going to talk about faster and more secure packages in OpenBSD because, you know, it's always better when it's faster, better, stronger and everything, you know. And I wanted to start with a very specific slide, I want to dedicate this to Antoine, who insisted on it. So Antoine Jacuto, the other guy who's maintaining way too many ports. And he wanted me to remind you people that OpenBSD is completely different from almost everything else. Like, we are not NetBSD, we are not FreeBSD, and we don't use the same package tools. In fact, I would like to say that for lots of features, we were there first. Everything is in Perl, and we've had functional updates since 2006. What this means, more or less, is that we've had lots of times to run into almost every problem you can imagine with this, and we fixed a lot of stuff that EuroBSDs are only discovering right now, or some of them might not even have a right clue about what's going on, actually. The other thing is that, as you can see, this is a desktop, well, a laptop computer, which is running OpenBSD, which is running just fine, including Wi-Fi, including suspend, including everything, and accelerated graphics. So if you want to use OpenBSD on a laptop, go ahead, it works. So, like I said, like I didn't say, but it was written, sorry, everything is in Perl. This was a deliberate design choice back in 2001 or something like that. And this gives us something which is really cool, which is that every tool in the tree uses the same interface, which means that when it comes for packing list, for instance, we don't have to reinvent the wheel each and every time, which is a problem which has plagued our systems for years, and which is probably gone by now, but very recently. Like, you don't have to write a few lines of awk to pass stuff again and again. Yeah, you do it every time with the same interface. If you know design patterns, it's a very simple interface, like you read your packing list into memory, and it's just a structured object composed of subclasses, and if you want to do anything, you just have to write a method that will traverse everything and do whatever you want. And we do that all the time, which means that you can do stuff that prints file names, or you can do stuff that checks for libraries, or you can do whatever with just a few simple lines of Perl, for instance. Another very nice features about the OpenBSD packages is that we don't have any cache at all. Like, I looked at other systems when I designed this, and it turned out that always synchronization problems. Either you put stuff into databases and you've got some file system check that fails and you're fucked, because basically your database is corrupted and you can't find anything in it. Or you get out of sync with upstream, or you get a mirror which has outdated packages and the database which doesn't match, and awful mess. So we just don't do that. We do everything on the fly. And there are two components to that. The first one is that we had to standardize package names so that you can figure out which is which by just looking at the file names. And the other part is that when you want to install a package or check for updates or anything, you just have to download what's needed and then you stop. Like, every package starts with a packing list, you've got all the information you need there, and if you don't need to go any further, you don't go any further, just in time. Now about signing stuff. It's actually something really old in OpenBSD land. Oh, sorry, I forgot about that. Yeah, this is more or less what I said. Oh no, this is something different. Yeah, also, we don't have transaction system with rollbacks. Actually, we check beforehand that everything works, and then we do the install. Like checking for size, like checking that every dependency is okay, and then only then we commit to actually installing the package. So we don't have a rollback system, and we don't need it. This is a part that never failed, actually. It works just 100%. So like I said, we had talks about signing stuff for a very long time. Okay, possibly not that long, but feels like that way, usually. The original idea was that if you look at gzip, actually, you can find stuff in the header. There's room to put whatever you want. So you could conceive that, for instance, you would rewrite an archive, putting a signature inside the gzip header, and boom, it would work. And nothing would care because nothing looks at gzip headers. Nothing should, at least. Some people went away with that. I think it was Duxong who wrote a small tool called gzsig, which kind of works. But it's not really good for us, because if you want to use this, then this means that you have to download the whole package first, and then you lose almost all the benefits that we had enjoyed for about 8 years by now. So we needed to do something else. At that point I hit a brick wall because it was really complicated to do signatures for OpenBSD, especially with a very hostile environment consisting of mostly Theodoret. And yeah, a bit of broadback, but as long as it's not too loud, it works. Yeah, kind of. So actually, the main incentive came from a third party for people at NTA who wanted to have signed packages, and it was quite liberating because it turned out to be simpler. Because instead of wanting to hardcode something that would cater to TO and stuff like that, I had to think about, okay, I have a provider who is giving me packages, and it has some identity, and I have to deal with that. And just putting those parameters in meant that, okay, I can do whatever I want, and then package will just say, okay, I want to use packages signed by this at this point. It's much simpler. So making it more general made me think about it some more, and I realized that I could solve a problem which I couldn't solve in a more specialized setting. Of course, we are talking about, at that point, X509 certificates, which is kind of a big issue, actually, of course. Okay, so how will it work? In contrast to gzsig, first let's talk about the positive aspect of it. We will just sign the packing list, so the stuff that's always downloaded anyway, because it's very small, except for TechLive, but then TechLive is a monster. And as soon as you have this packing list signed, you're okay for the rest of the package, because the packing list contains hash for every file in the archive. So then you can do just-in-time extraction. You just have to be really careful to make sure that you don't do anything with any given file before you've checked its actual hash. So the algorithm goes, get the packing list, check the signature. Okay, the packing list hasn't been tampered with. Then you can extract a file, check the hash, do whatever you want with that file, and keep going for the rest of the package. And then you're done. Boom, it works. Of course, the devil lies in the details, as usual. What about the metadata? You have to be also really careful that you are going to record everything that you need in the packing list. Like, for instance, if you've got a file which is setuid, you have to record that in the packing list. So we have lots of checks about that in the OpenBSD package system. When you create package, you check that everything is indeed written explicitly in the packing list, so that you can then audit manually stuff, make sure that you haven't created a package which contains a setuid file by accident. This is probably the most important part, because you will later check that package, but you definitely don't want to create that information automatically. You want to have somebody who will check that the new version is intended to have a security file. When this stuff changes, it's written in the packing list that's recorded inside CRS that needs to be committed by someone, so that somebody will have at least a clue that this file is set ready for a reason. And of course, there's a second check later when you're going to add that package on your machine. You will verify that everything in the table is actually properly recorded in the packing list. Otherwise, you say that there's something really fishy going on. I know that for OpenBSD we love fishes, but not these ones. What's cool about this is that this issue was actually pretty much linked to being able to build stuff without root, like being able to do the fake install before you do the packaging. And so it kind of meshes together. When we worked with Nadi to try to do a fake without sudo, which works 100% for about 2 years now, we realized that, okay, we have to make package add, package create, everything in steps so that everything will work. Let's talk about those certificates some more. This was probably the most annoying part of it, but funny. It's a pity that Tedo isn't in the room, because he would have probably more to say about that. Like OpenSSL is a complete shit show. For instance, if you look at signing stuff with OpenSSL, there's this quirk where when you do signatures, it will automatically convert files from Unix to standard RFC stuff, like with CAD written on new lines. But when you try to check signatures, it doesn't do it automatically. And so you create signatures, you check them, and it fails, and you have to add an extra exchange so that the check works. It's just so completely wacky. It looks, yeah, that was me trying to figure that one out, more or less. There's also the fact that PKI are really complicated. We had to explicitly add some documentation to that. And contrary to popular belief, you should be in the other room if you want to talk about documentation, but OpenBSD doesn't like too much documentation, especially stuff that makes absolutely no sense whatsoever, like PKI. So, of course, we're going to talk about the next part, which is Signify, which came out of the blue because suddenly Tedo decided he wanted to do something with that part of crypto. And it ended up being Signify, which is a very simple tool, which has some very specific design. Like, for instance, it doesn't have anything to support PKI at all. It's definitely not the goal. It's a good thing, because PKI are complicated, nobody understands them, everybody fucks them up. Look at GPG, and they got at least $2 per release, I guess, at most. And so, not having PKI is actually an advantage in this situation. Whereas also this funny story, because Signifier came about because they got pissed at something again. Like somebody was bragging about OpenBSD being really secure on the mailing list, and some guy said, but you still don't provide signatures and package sign and everything. And for years and years, they did say he didn't care about signing anything. And I don't know, but this time he got pissed, and in 3 months, things started moving, and he wanted to have everything signed in the release. It was very funny. We've probably seen this already, but Signify looks like this. This is a signature for an older OpenBSD release. It's been a year. And you can see that the signature, which is the second line up there, is very short, especially if you compare that to classical signatures like X509. It's only a line long. You could almost remember that. Almost. Since we don't have any PKI, you have to design things to work with that. The thing you actually need to do is you need to think about who's going to sign things and set things up accordingly. Yeah.
Then I noticed that this is apparently using the package key to sign a snapshot. Is that an accident or is that a slide?
It's probably that I did this on my own somewhere or something, I don't remember.
Let's make sure it's
Yeah.
Yeah. Yeah, it's something else I want to talk about. The actual technical part isn't that complicated. The difficult part about that thing is really making sure that people who are going to use this actually understand what's going on, which is the main problem with cryptography these days. Like, everybody is clicking on the web and saying, oops, this certificate hasn't been signed, or there's some problem with this connection. I don't care, I just want to get there. And then they get some technical messages that they don't understand, or they do understand part of it, and they don't give a fuck anyway because it's got fucked up. So we're trying really hard to make it simpler and to make it workable. It's not 100%, sometimes accidents do happen, but it's much better than it used to be. So, about this, the idea is that you are going to get one key for one usage pattern. I don't know if I should talk about this, but we have 3 people in the OpenBSD project who are actually in charge of signing every part of it. Like, someone is signing the main release, somebody else is signing the very special packages that correspond to firmwares that we can't redistribute because of stupid legal reasons, like Intel is a bunch of morons in that regard, for instance. And we've got a 3rd key, which is actually used to sign packages, and that's it. Oh, Ted, I didn't see you, sorry. So this means that for packages, we are going to get a very specific key which is only used to sign packages. Of course, we don't follow PKI, so we don't have signing parties or anything. How do you know that you can trust our key? Well, just because it's published on about every channel. That's another advantage of Signify. The keys are short enough that you can publish them anywhere, and it's very easy to check. So for any release of OpenBSD, you're going to get 3 keys, and they are going to be everywhere, on the CD, possibly on the t-shirt. I haven't seen them yet. On Twitter, everywhere, and this is the same key. If one of those keys doesn't match, somebody will notice very quickly. There was this one thing which wasn't already in the mix when I built the first version with X509 certificate, which is that the build process is actually disconnected from the signing process. Like, you've got the specific machines on which you transfer packages, and it's completely disconnected from the network. And then you sign those packages, and then you put them back elsewhere. And yeah, of course, there is no revocation process. It's not a PKI. For the story, I look at 6509 certificate revocation list and shit like that. And I didn't have enough painkillers. I couldn't figure out how it works, so we still don't have those for X509, and I don't think anybody gives a fuck anyway. Let's compare things in package length to how it happens in release. There's one major difference, which is that for release you've got a global file which is signed once and for all, whereas for packages, each package is signed individually. We could do the same thing, but again, see back a few slides when I was talking about this caching issues, this would get out of sync, because you have to realize that the release is very small comparatively, and the set of packages, about 9,000 packages that we have, it's something like, I guess, 30 gigabytes or so. So when you synchronize your mirror, sometimes you end up being in the middle of a sync with half the last snapshot, half the new snapshot. How do you get the signatures? Like for instance, you could decide that you update at one specific time when you're sure the mirror is okay, and the rest of the day, well, basically you're fucked. So it doesn't work that way. You have to sign each individual package. There's no way we could do a full bulk transfer to mirror each and every time, especially since some of the mirrors probably don't have enough room to keep the old set of packages and the new set at the same time. So there's an obvious issue with signing packages after the fact, which is that if you want to sign, you have to unpack your package, then sign, then repack. And it's very slow. The unpacking and repacking is the part that's actually slow. And there is a solution. Remember when I talked about JZSig at the start? I had to look at this a few years ago, and I remembered something, which is that actually gzip has a very cool characteristic which you might not know about, which is that you can actually put several gzip files next to each other, and if you call gnzip on them, it won't care. It will just unpack each segment separately, concatenate the results, and you end up with a single file. So we are actually now using this. Like when we build packages, we start compressing the package, then we stop at the end of the packing list, and we start gzipping again from scratch here. And so you end up with a WAD file, which is a complete table, which is actually compressed separately, so that you can extract the packing list only, sign it, recompress it, and then you just have to copy the rest of the stream transparently without needing to do anything about it, and it works. This is not anecdotal. This is a huge improvement. Like the first time we tried sign packages, it was on this box, I guess. Before this, it took, I guess, 2 hours and a half to sign the full collection of packages. And I tried to parallelize stuff, but it didn't work all that well. It turns out that gzip is really intensive on your processor. And I guess that I went probably from 2 hours and a half to 2 hours, something like that. And with chunk gzip, we went down to 20 minutes over the same collection. So this is definitely something to think about. And everything outside of the package tools doesn't even need to see that. Like you star on one of those packages, it won't even notice that there are several chunks. Just like that. Also the obvious question, what to do if we ever move to another scheme like bzip2, for instance, or XZ? Well, it works just as well. The guys who designed those new compression protocols thought about it, and they put the exact same features in both those tools. So you're looking forward to a feature. It works. More properties related to the actual signing process. Like I said, it's in Perl, so it means that in order to sign the packing list, what you do is you call a specific method which writes everything in the packing list except for the signature. Like you have a blank signature and everything else is written as usual. This is what you pass to Signify, and that will get signed. And then you just have to reincorporate the result inside the resulting packing list and put it in the table. This means that everything gets signed, including the name of the key, including the timestamp at the time this was signed, which can be very useful. As far as performance is concerned, obviously, when you sign packages, you don't need to do anything except extract the packing list, compute the signature, and repack the packing list. Everything else has already been done during the build process, like computing hashes for every file. Of course, that's part of the build process. There's absolutely no... there is some security involved, but there is no hard security involved where you really don't want to leak your credentials. or anything. So this is very simple. There is this issue about consistency. Since your package collection can be synchronized at different times, how do you deal with it? We actually have this mechanism in OpenBSD, which is called quirks. Quirky name, yeah, of course. Which is a very specific package which always gets updated. So each time you update quirks, packaged will actually give you the timestamp at which quirks was signed. So you know that at least this package was signed on one particular time. And quirks contains a lot of things, among which there is a list of risky packages. Like for instance, if you have some security update to something, then every quirks posts the security issue will alert you that a package which is before this version is a problem. And if you can't find an update, then there's somebody who is playing funny games with your mirror, so you're safe. Yeah, let me talk a little bit more about quirks. Funny name, yeah. Okay, right, there's a small database of stuff related to packages, like for instance, when you rename stuff, the tools can figure it out. This is something that I actually hate. I would very much prefer that we keep the same names forever, but at some points there are people, especially in GNOME land, who are moving forward and changing stuff all the time and changing names, and sometimes it's too much trouble to try to keep updated names, and so I gave in and okay, let's do this. It's still very small because it's just a bunch of PRM methods with maybe, I guess we have something like 200 exceptions these days or something like that. And since it's actually code with just a hash table in the middle, you can script things if everything is going the same way. Like for instance, you have 10 packages with almost the same name. You can say, okay, use this bunch of names and do the same transformation each and every time and it will work. It can also be used in some really strange cases, mostly with one of the developers at Barrett, who almost always manage to do stuff from big packages that are very difficult to make work. And sometimes when the update fucks up because some files which should be under the control of the package systems are not, like take-life formats and shit like that, you actually can go into the file system and fix this on the spot, like adding stuff from existing packing lists on the install system and then doing the update. Okay, that's really quirky, but it's really useful. In the end, there's no way around it. If you want your system to work, you have to have this kind of hack. Yeah, basically I can't predict the future, so I need to have a cat that gets me out of jail for free. And that's what Quirks does. I can add stuff here, I can add code, I can re-implement parts of package add if I need to, on the fly, without needing to touch the basic system, so that everything will work. I have to apologize because I looked again before this conference for this paper. I remember reading something about this attack, about packaging system, where you would block part of the mirror so that you wouldn't get security updates. And the part about always displaying the date for quirks and having a list of insecure packages in it is specifically there to block it. But unfortunately, when you try to Google for insecurity in package systems, you end up with lots of stuff with actual physical packages that you send through the mail, and I wasn't able to find back this paper, otherwise there would be a reference there. Hello, give me the next slide, thank you. So again, the solution is to deprecate packages in the Quirks package, and since we don't really know how often packages will be updated, since it depends a lot on the architectures, like for instance a week ago Vax finally managed to finish its package collection for 5.8, about 2 months after everything else, something like that. Yeah. Send kudos to Sebastian, he's the one responsible for that. All we know about the Quirks timestamp is displayed. Like if you see that your Quirks has been signed a month ago and you want Spark 42, it's probably okay. But if you see that it has been signed a month ago and you are on MD64, it probably means that there's something very strange going on and you should really worry. Also, I have to say that we try to keep things transparent so that the actual user is in control of what's going on, and hopefully this will make things better. People will understand what's really going on. We definitely don't want people to have the impression that we guarantee anything that we don't guarantee. All the security system gives us is tell you whether the package that has been built on the developer's machine is actually what you get, and nothing more. That's really important. There are still some issues with some OpenBSD packages. There are 9,000 packages and about 30 active ports developed, more or less. So yeah, I'll let you do the math and you can figure out that we can keep up with everything. Not all the time, unfortunately. I had a question about this a few months ago. Like Emmanuel Dreyfus told me that, but you actually do revocation. No, this is not revocation or anything. It's just about how packages work, and this has nothing to do with the signature and the signature being wrong. It has everything to do with there being a security hole in your package, and just saying, okay, you really need to update this one, and if you can't find a new one in this mirror, that means that somebody has been tampering with that mirror and you need to go elsewhere. I hope that's crystal clear by now. Do I have enough time to do a small sidetrack? Yeah, looks like it. Oh, that's cool. There are a few things I still need to talk about. This is just the slide. You could actually apply the exact same process to tar. Actually, have parts of a proof of concept that work. You could do a tarball that would get just-in-time checking instead of downloading everything, checking the signatures and everything. What you do is you take your tarball as a binary file, and each chunk of the tarball, which means the metadata, the header plus the actual data, you just have to compute a checksum for it, like 256 for instance. This gives you a kind of a manifest file that you can prepend to the tarball using the exact same technique, using chunk gzip again, and you just need to sign that. So you just fork off a signify process to sign it during creation. Well, actually, you create your tarball, then do the sign part and put everything together. During check, you just need to, as soon as you see a manifest, check that it's indeed signed correctly. And then after extracting each file, you check that the checksum is okay. And then you're home free. This gives you just-in-time signatures for tarballs. Well, the only reason I haven't finished this is that nobody shown any interest yet. No practical use so far, and I have already too many things to do. So if somebody wants to play with it, it's very simple. It's probably, I guess, half a day or 1 day to bring it all together, and probably 2 months to convince other OpenBSD developers that it belongs in the tree. That's going to be the hard part, as usual. So, just a thought. Okay, so I've talked about the more secure packages. I've talked about the fact that we are fast to begin with, especially considering its power. What about faster packages? That's the cool part. That was a side effect that I didn't foresee. This work made me think about the fact that we already have checksums for every package, for every file in a package. So we can actually use this information, and we do use this information now. The idea is that you don't have to keep everything in order inside the package. Like for instance, when we did updates, what you do is first you extract everything from the new package, then you perform the actual update, which means running the whole packing list for deleting stuff and running exec command and stuff like that. And then you move the new things in place and you execute the commands. You have to do it that way because if you want to guarantee that everything will work, you first have to extract all the new files under temporary names in case your network goes down and you can bring it back up, for instance. And then you can replace the old package with a new one. So the thing we did is that we made sure that every installation and update proceeded along the same lines. Like we always have to, these days, to extract things to temporary files first, and then perform the actual installation, and then we can reorder packages. We can put files in whatever order we want inside the package. Everything will get extracted on the disk, then move into its proper location, and then we traverse the packing list in order to run everything that's needed. The starting thing was that it was actually very small to do. I thought that at first it would be complicated, I would need to keep lots of information. Turns out everything you need is just the list of checksums of the files. You don't even need the names or anything. You have the list of checksums for the files inside the package at a given time. You keep it at first in the order in the packing list, and then you compute the new one and you compare checksums. And everything that hasn't changed is going to move to the end. Everything that did change is going to stay at the start. That's it. You don't even need the names or anything. That's very funny. Think about it. It works that way. Oh, sorry. Oops. How do I get to the last one? Oh, well. Yeah, that was the last one. Okay. Okay, so this works, and this works really well. Like, if you use it for big packages that don't change all that often, I'm always thinking about Tech, for instance. Tech Live is a very good example of that. When you do an update, instead of getting 200 megabytes file or something like that, yeah, you will probably get 10% of that. What's very surprising is that it works actually on lots of packages. Like, for instance, if you look at GTK or stuff like that, very closely, you will notice that half the file inside one of those packages are actually icons or text stuff or translations that don't change that often. So I was very surprised by noticing after this change that in many cases, when you do an update, you will down maybe 20% of your package size. And what's even better is that the more often you update, the better it is. Because if you wait for 6 months, of course, there are lots of packages which will have actually changed by a lot. But if you do update every week, then maybe you will have all your packages updating because there are new versions, small differences, small tweaks into each and every package. But all the text information, more or less, will be the same. It could be even better, but there's one thing that we are not really good at yet, which is to be able to rebuild the same thing consistently every time. So if we can get rid of more timestamps and stuff like that, it would be even better. It's probably just a small percentage. It's not that good anyway. There are other good reasons to be able to do consistent builds, which are much more important than just doing this. And finally, last part, was also thinking about the mirrors. Okay, so if you do a fan out, you've got about 40 to 50 gigabytes for, I guess, MD64 and i386, something like that. And since those are tables which are compressed, trying to do any scheme like rsync isn't going to fly. You can't reduce the bandwidth from it, because since it's compressed, as soon as the information will change, then you're fucked and you're not able to not transfer the rest of the file anyway, even if nothing did change. I should mention that there is a specific version of no, there are specific versions of zlib libraries which actually offer some kind of support for async. But is there anybody in this room who's looked at it already? Nope. Don't look. It's just crazy. The patch is completely different on each and every one of those library versions. It changes all the time. It's not an official patch. And I think that the only OS who might be crazy enough and has enough manpower to do that would be Debian, probably, because they don't care, they have enough lemmings to throw into this and it will work anyway. So the idea about signing packages gave me another idea, which is that now that we have packages in the right order with a file that don't change at the end, we could extend the chunkable gzip idea and rebuild our packages not just as one chunk for the signature and one chunk for the rest of the package, but as lots of chunks starting from the end. Well, I applied the stupid physicist idea. I just decided, okay, let's put 8 files in each chunk. And then if a whole chunk doesn't change, because it's composed of the files that didn't change, of course, at the end of the package, then it will be the exact same file for gzip, after gzip. So I think we'll see it, and it will be able to not transfer it again. Of course, you need numbers for that. Like using chunk gzip means that, of course, you're going to lose a little bit as far as compression size goes, because you're going to compress from scratch for each chunk. Turns out it's really small, 0.5% size difference. And on the other hand, it's really good for low bandwidth mirrors, because you gain about, I guess, 30 or 45% on a typical transfer when things don't change all that much. Of course, there are some details, like tar header used to have timestamps for every file. So we've actually moved that to the packing list. And if you look at the new package on OpenBSD, you'll notice that everything is dated from January 1st, 1970. Small price to pay. I guess that still having something that looks like a turbo is a good idea, but unless you're stranded on a desert island, you're not going to use it for any useful purpose anyway. You're going to get through the actual package tools suite to manipulate those packages, so we don't care. I think that's it. I hope I didn't forget anything. And I'm even a bit short by 2 minutes, so if you have any questions, now would be a good time. Yeah?
It's probably not the same, like the same part of the system, but talking about secure package. When I, as a end user, want to install something or update something, and I'm very much security, it could occur to the thought that it is also a question of security, that I want an eavesdropper not to know what I install, even if the package is encrypted. The length of the packet is probably characteristic. Are there some thoughts of looking into a feature that some random length of padding is added to some packet so that it is not clear which packet it is?
Okay, the question was, since we have secure packages, that means that they can be tampered with, but of course that doesn't deal at all with well, confidentiality question that some eavesdroppers could look at the network and see which packages I'm transferring, even by the size or something of it, and deduce that I'm running this and this on a machine, and I wouldn't be able to do anything about that. I admit that I haven't dealt with that problem at all, and I don't know how to do that. I guess that's probably outside of the package system purview. If you want to do that, you probably want to use a VPN and transfer your packages beforehand, and so that nobody would be able to see anything. It's completely outside of the system. That's a good point, but I'm pretty sure I don't see any way to deal with it within the package system proper. You have to go to the network and do a proper VPN or something to be able to achieve that. Sorry.
You can download all the packages. Yeah, that's an easy solution.
Yeah, you can download everything, of course. Yeah, another question? Oh, yeah.
I don't understand the package saving mechanism because on the package server I have to complete touches at all, and now you say you will download only parts of it, the change tiles for the rsync. Ah, okay,
Okay, the question was how does it work for solving bandwidth issue with the mirrors? Just making rsync work with compressed files, which it doesn't do by default, and you can either adapt your compression library, which is a complete nightmare, or you can figure out a way to make sure parts of the file don't change, and then you leave it to rsync to decide which part won't change. So the people who are actually using this on the mirror, they have some specific parameters for rsync because we have an idea how big each chunk of a file is going to be. So you set up your, I don't remember, your block size for rsync to be in that ballpark instead of the default, which is 3000 bytes or something like that, which is way too small for what we're doing. And then you get a huge bandwidth saving. I guess that I got mostly numbers from Stuart Anderson about this. I think he's managing, or he knows some people who are managing some mirrors in some parts of the world where bandwidth is actually a problem. So if you want to get new snapshots in a timely manner, this is good because you end up from being able to transfer a snapshot in 30 hours to something like 15 hours or so. Yep. Other questions? Oh, everything was clear? Or you didn't understand anything? I don't know. Yeah, that's your solution that possibly nobody cares, but yeah, pretty sure about that. Yeah, I'm sure that you actually care about having packages that update faster.
Absolutely. Because I'm so short on memory.
Right. Okay, so thank you guys.